There is a mountain in northern Chile where the air is so dry that clouds forget how to form. It rises out of the Rio Hurtado Valley, a spine of pale rock above a landscape that looks less like Earth than like a rehearsal for Mars, and on top of it sits a telescope that is not particularly large, not particularly famous, and not particularly beautiful. It is a squat white dome housing a half-meter mirror. It cost less than a modest house in California. It has no crew. It does not wait for astronomers to arrive. Every clear night, and almost every night here is clear, it opens its shutter on its own and begins to sweep the sky in long mechanical arcs, photographing the same patches of darkness again and again, comparing each new image against the last, looking for one thing and one thing only, something that has moved. On the first day of July in the year 2025, it found something that had moved. The detection was, at first, entirely unremarkable. A smear of light too faint to see with any backyard instrument. A handful of pixels shifted a fraction of a degree against the fixed stars of Sagittarius. The software flagged it and pushed it to a public database, where it joined the thousands of other rocks and ice fragments that this survey and its siblings discover every year. The object received a provisional designation, a string of letters and digits with no poetry in it at all. It sat in a queue. Somewhere in the world, an algorithm began the routine work of fitting an orbit to 3 data points, and if that orbit had come back looking like every other orbit, this object would have been catalogued, numbered, and forgotten by everyone except the small community of people who care very much about small icy bodies. The orbit did not come back looking like every other orbit. Within hours, additional observations were pulled from archives, images taken days earlier by other surveys that had photographed the object without recognizing it, the way a security camera records a thief walking past without knowing it has done so. With those extra points, the arc lengthened and the fit tightened, and the number that emerged from the mathematics was so far outside the expected range that the first reasonable assumption was an error in the data. The number was the eccentricity, and to understand why that number stopped astronomers mid-sentence, you have to understand what eccentricity is, which is really a question about what it means to belong to something. Every object gravitationally bound to our sun travels on a closed loop. Not necessarily a circle, almost nothing in space moves in a perfect circle, but a closed curve nonetheless. An ellipse, a racetrack that always brings the traveler home. Earth's racetrack is nearly circular. Mars leans a little more. Pluto's is stretched and tilted enough that for 20 years of its 2.5-century lap, it comes closer to the Sun than Neptune does. Comets from the deep freeze at the edge of the solar system run on ellipses so elongated they are almost needles, plunging inward from 100,000 times the Earth-Sun distance, whipping around our star in a few frantic months, and then climbing back out into the dark for tens of thousands of years. Halley takes 76 years to come around. Hale-Bopp, which stunned the Northern Hemisphere in 1997, will not be back until roughly the year 4385. Eccentricity is the single number that describes how stretched that loop is. A perfect circle has an eccentricity of 0. Earth's orbit is 0.017, so close to circular that if you drew it accurately on a page, your eye could not tell it from a circle. Halley's Comet is 0.967, an extreme stretch, a needle, and yet still, crucially, a closed shape. Everything in our solar system, every planet, every asteroid, every comet, every grain of dust that has ever been catalogued, has an eccentricity below 1. Below 1 means bound. Below 1 means home. Below 1 means that no matter how far you wander, the sun's gravity has a grip on you and will eventually reel you back. At exactly 1, the loop opens. The traveler is moving at precisely escape velocity, and the curve becomes a parabola, an open shape that goes out forever and never returns. Above 1, the shape becomes a hyperbola, and the object is not merely escaping. It is escaping with speed to spare, moving faster than the sun can ever undo, arriving from infinity and departing toward infinity, passing through our solar system the way a bullet passes through a room. The new object's eccentricity was slightly above 6. Not 1.001, the sort of value you get when a comet on a long ellipse gets a small gravitational nudge from Jupiter and is flung out of the family. Not 1.2, the kind of number a slightly aggressive interpretation of noisy data might produce. 6.1. A number so far past the boundary that no plausible measurement error, no gravitational encounter with any planet in our system, no imaginable local history could have produced it. This object had not been kicked out of our solar system. It had never been in our solar system. It was falling through, and it had been falling for a very long time, and where it came from was not here. That is the moment. That is the instant when a smear of light on a robotic telescope sensor in the Chilean desert became one of the most consequential objects in the history of astronomy. It was given a permanent name that carries its status in its first character, 3I/Atlas. The 3 for third, the I for interstellar, Atlas for the survey that caught it. Third, in the entire recorded history of human skywatching, the Babylonian tablets, the Chinese court astronomers who logged every guest star for 2,000 years, Tycho Brahe measuring positions to the limit of the naked eye, the great photographic surveys of the 20th century, the digital era with its billions of images, the third confirmed visitor from beyond. And then, over the following 18 months, as the largest telescopes ever built by our species turned toward it one by one, 3I/Atlas did something that neither of its two predecessors had done. It let us read it. It came in bright, it came in close, it came in early enough that we had months to prepare, and it came in gushing gas. And in that gas, spread across the infrared spectrum like text on a page, was a chemical composition that did not match anything. Not any comet in our solar system. Not any comet in either of the two great families. Not the ices in the clouds between the stars. Not the material in the young planet-forming disks we photograph around other suns. The carbon dioxide was wrong. The metals were wrong, and wrong in a way that on Earth requires an industrial chemical plant. The heavy hydrogen was wrong by an entire order of magnitude, 10 times outside the range measured in every comet humanity has ever sampled. The carbon isotopes pointed to a chemical environment that has not existed in this galaxy for something like 10 billion years. The nitrogen isotopes pointed somewhere colder and more remote than any place where planets are supposed to form. Every one of those measurements was made by a different team with different instruments using different physics, and every one of them pointed the same direction, toward a body that assembled itself in a place profoundly unlike the place that made us, under a star profoundly unlike ours, at a time when the Milky Way was a different galaxy than the one we live in now. This is the story of what came out of that chemistry. It is a story about a piece of debris smaller than most American cities, traveling at speeds that would carry it from New York to Los Angeles in about a minute, which arrived carrying a chemical signature that forced a generation of scientists to open the textbook of planetary formation and start writing in the margins. To feel the weight of what happened next, you have to know what came before, because 3I/Atlas is the third, and the first two are the reason the third mattered so much. In October of 2017, a telescope on the summit of Haleakala on the Hawaiian island of Maui caught a fast-moving point of light that had already passed its closest approach to the Sun and was on its way out. It too had a hyperbolic orbit. It was the first object ever confirmed to have come from another star, and it was named ʻOumuamua, a Hawaiian word for a scout or a messenger sent from the distant past. And it was a nightmare. Not because it was dangerous, it was never remotely dangerous, but because it was almost perfectly designed to frustrate us. It was small, perhaps a few hundred meters across. It was faint. It was discovered late, already receding, already dimming, and within weeks it was beyond the reach of every telescope on Earth. Humanity got about 11 days of decent observation on the first object ever confirmed to come from another solar system, and then it was gone forever, out toward the constellation Pegasus, never to be seen by anyone again. In those 11 days, it managed to be strange in almost every measurable way. Its brightness swung wildly as it tumbled by a factor of 10, which implied an extraordinarily elongated shape, something like a cigar, or, in an equally valid interpretation of the same data, something like a pancake or a shard. Nothing in our solar system is that elongated. It showed no coma, no tail, no dust, none of the visible outgassing that defines a comet. And yet it accelerated. As it left the inner solar system, it was pushed outward, slightly but unmistakably, by a force that was not gravity. In an ordinary comet, that is a trivial observation. Comets are ice. Ice near the sun turns to gas. Gas escaping from one side of a nucleus acts like a small, sloppy rocket engine. Astronomers have accounted for this in cometary orbits since the 19th century. But ʻOumuamua showed no visible outgassing at all. Something pushed it, and nothing came off it that anyone could see. The proposed explanations ranged from the reasonable to the extraordinary. Pure hydrogen ice which sublimates invisibly, nitrogen ice, making it a fragment blasted off the surface of an exopluto. An object so absurdly low in density and so fluffy that sunlight alone could push it. A cosmic dust bunny the size of a football field. And, from one Harvard professor whose name will return to this story, the suggestion that it might be a manufactured object, a light sail, a piece of alien technology dead and drifting. We will never know. That is the central tragedy of ʻOumuamua, and it is the fact that shaped everything that followed. The first interstellar object ever detected was studied for a week and a half and then vanished into permanent darkness with all of its secrets intact. Astronomers do not like being taunted. 2 years later, in August of 2019, an amateur astronomer in Crimea named Gennady Borisov, using a telescope he had built himself, found the second one. 2I/Borisov was the opposite kind of object in almost every way. It was unmistakably a comet, fuzzy, active, spouting gas and dust, growing a proper tail. It was discovered inbound, months before perihelion, giving observers real time to prepare. And when the great telescopes examined it, they found something almost disappointing in its familiarity. Borisov looked chemically a great deal like a comet from our own solar system. Water, cyanide, diatomic carbon. It was somewhat enriched in carbon monoxide, and it carried an odd abundance of nickel vapor, but broadly it fit. The lesson drawn from Borisov was reassuring, almost cozy. Comets are comets everywhere. The chemistry that built our solar system appears to be a fairly universal recipe. Other stars make the same kind of dirty snowballs we do. Two objects, two utterly contradictory lessons. The first said that interstellar space sends us things so alien we cannot even classify their shape. The second said the galaxy is full of familiar snowballs. A sample size of two disagreeing with each other, with one of the two already unreachable forever. This was the state of the field on the 1st of July 2025. And then came the third. The first thing that distinguished 3I/Atlas was timing. It was found at roughly 4.5 astronomical units from the Sun, beyond the orbit of Jupiter, out where sunlight is weak and cold and thin, and it would not reach its closest approach to the Sun until the 29th of October, nearly 4 months later. For months of warning. For months to write observing proposals, to convince telescope time allocation committees to interrupt carefully planned schedules, to coordinate across continents and space agencies. In the world of astronomy, where the largest instruments are booked years in advance and every hour is fought over, for months is an eternity and a gift. The second thing was brightness. 3I/Atlas was bigger than its predecessors and far more active. Estimates of the nucleus size ranged widely, as they always do when a solid body is buried inside a glowing cloud of its own exhaust, perhaps a few hundred meters, perhaps several kilometers. But the activity was undeniable. At 4.5 astronomical units, where water ice is far too cold to sublimate and most comets are inert lumps, 3I/Atlas already had a coma. It was already venting. Something inside it was already boiling. That alone should have been the first warning that this object was not going to behave. And the third thing was geometry. Its path would bring it inside the orbit of Mars, sweeping past the red planet close enough that the fleet of spacecraft in Martian orbit, machines built to photograph dust storms and map minerals, never designed for this, could turn and stare. It would pass through the inner solar system in the autumn of 2025, then swing out and remain observable, dimming slowly, for many months afterward, all the way through 2026. So the world got ready. Proposals were filed on the James Webb Space Telescope, the most powerful infrared observatory ever constructed, a gold-plated eye at a gravitational balance point 1 million miles from Earth. On Hubble, on the Very Large Telescope in Chile, for 8-meter giants standing together on a mountaintop. On Keck in Hawaii, on Gemini, on the Nordic Optical Telescope, on radio arrays, on the ultraviolet detectors aboard the SWIFT satellite, on SPHEREx, a newly launched NASA mission designed to map the entire sky in near-infrared colors. Amateur astronomers with backyard rigs in Arizona and Texas and Florida contributed astrometry. Every serious instrument that could point at it did. For the first time in history, humanity was going to get a good, long, patient, multi-wavelength look at a piece of another solar system. Nobody expected it to look like this. Before we can talk about why the chemistry of 3I/Atlas broke the model, we have to talk about the model. Because the phrase rewriting the laws of physics is thrown around carelessly. and it deserves a moment of honesty right at the start. The laws of physics are not in danger. Gravity still works. The conservation of energy is intact. Nothing 3I/Atlas has done requires new forces or exotic particles or a revision of general relativity. Anyone selling you that story is selling you something. What is in danger, what has, in fact, already been substantially damaged, is something more interesting than a law. It is a model, a story we told ourselves about how solar systems assemble, where their ingredients come from, and how universal our own experience actually is. Laws are the rules of the game. Models are our guesses about how the game has been played across 100 billion star systems based on the single game we happen to be sitting inside. And the model of how comets form was built almost entirely from a sample of one. That model is worth laying out properly, because it is genuinely beautiful, and because you cannot appreciate a shock without understanding the expectation it violated. In 1950, an astronomer at Harvard named Fred Whipple proposed that comets were not, as many then believed, loose-flying gravel banks. They were, he argued, single solid bodies made of ice with rock and dust mixed through them, the dirty snowball. A phrase that has survived 75 years of refinement and remains roughly correct, though modern researchers prefer icy dirtball, since by mass most comets are more dirt than ice. Whipple's insight explained the puzzle that had haunted cometary astronomy for a century. Why comets do not follow purely gravitational paths. Ice on a warming surface turns directly to gas, that gas rushes away, and by Newton's third law the nucleus is pushed the other way. A comet is a rock with a leak, and the leak steers it. The next question is where those ices came from, and the answer is one of the most elegant ideas in all of planetary science. It is called the snow line or the ice line, and once you understand it, you understand the architecture of every solar system in the universe. Picture a young star, newly ignited, surrounded by a flattened disk of gas and dust, the leftovers of the cloud that collapsed to make it. This disk is hot in the middle and cold at the edges, for exactly the reason a campfire is hot in the middle and cold at the edges. Now consider a single chemical compound in that disk, say water. Close to the star, it is far too warm for water to exist as ice. Any water molecule is a free-flying vapor. Move outward, and the temperature drops, until you cross a specific distance where water can freeze onto dust grains and stay frozen. That boundary is the water-snow line. In our own solar system, it sits somewhere out past Mars, around 2.5 to 3 times Earth's distance from the Sun. This is not a minor detail. It is arguably the single most important line in the solar system. Inside it, solid material is limited to rock and metal, which is why the inner planets, Mercury, Venus, Earth, Mars, are small, dense, dry worlds. Outside it, suddenly there is vastly more solid material available, because water is enormously abundant and now it counts as a building block. That surplus is why Jupiter could grow massive enough to capture hydrogen directly from the disk and become a gas giant. The snow line is the reason our solar system has the shape it has. It is the reason there is an asteroid belt and not a fifth rocky planet. It divides the family. Now the crucial part. Water is not the only compound with a snow line. Every volatile substance has its own, at its own distance, set by its own freezing temperature. Carbon dioxide freezes at a much lower temperature than water, so the carbon dioxide snow line sits much farther out. Carbon monoxide is more volatile still. It needs to get down to roughly 20 or 25 degrees above absolute zero before it will freeze, so its line lies farther out again, in the deep cold beyond Neptune. Methane, nitrogen, ammonia, each has its own boundary. The result is that a young solar system is a set of nested chemical zones, like the rings of a tree or the layers of an onion. Where a body forms determines which ices it can incorporate. A comet that assembled just past the waterline will be mostly water ice with very little else. One that assembled far out beyond the carbon monoxide line will be loaded with the most volatile compounds in nature. So a comet's composition is a birth certificate. It records the temperature of the place where it was built, which records the distance from its star, which tells you where in the architecture of a solar system this particular piece of debris was assembled. Read the chemistry, and you can place the object on a map of a world you have never seen. That is the theory. Here is what it predicts in practice, and here is the number that matters most in this entire story. In the comets of our solar system, water is the dominant ice. Overwhelmingly. Typically, water makes up 70 to 80% or more of the volatile content of a cometary nucleus. Carbon dioxide is present, sometimes in significant amounts, but it is a minority component, usually somewhere between a few percent and perhaps 30% of the water abundance. Carbon monoxide is generally less again. When comets swing in from the outer solar system and begin to heat, water sublimation is what drives the show. Water is the engine. Water makes the coma, water makes the tail, water is the reason we can see them at all. That pattern has been confirmed across the whole cometary population, Jupiter family comets, which orbit on relatively short loops and are thought to come from the Kuiper belt beyond Neptune, and long-period comets, which fall in from the vast spherical Oort cloud that surrounds the solar system out to a light-year or more. Different reservoirs, different histories, different orbits, and yet broadly the same chemistry. Water first, everything else second. It held for Halley when a European spacecraft flew past in 1986. It held for Comet Hale-Bopp. It held, in extraordinary detail, for Comet 67P/Churyumov-Gerasimenko, which the Rosetta spacecraft orbited for 2 full years, riding alongside it through perihelion and measuring its exhaust molecule by molecule with a mass spectrometer, the most thorough chemical analysis of another world's building material ever performed. That Rosetta mission deserves a sentence of its own, because it is the benchmark against which everything in this story is measured. For 2 years, from 2014 to 2016, a European spacecraft flew in formation with a comet, matched its velocity, orbited it, dropped a lander onto its surface, and rode alongside as it approached the sun and came alive. It watched jets erupt from cliffs. It measured the composition of the escaping gas continuously, molecule by molecule, as the comet warmed. It photographed the nucleus in detail down to the scale of a few meters. A black, cratered, double-lobed body shaped like a rubber duck, so dark it reflects about 6% of the light that hits it, so porous that its density is less than that of water ice, riddled with voids. Rosetta did not merely study a comet. It defined what a comet is. Every number in the modern cometary inventory, the abundance of each volatile species, the dust-to-gas ratio, the isotopic ratios, the presence of glycine and phosphorus and dozens of organic molecules, traces back in some measure to those 2 years. When we say 3I/Atlas is unlike a comet, the comet we most precisely mean is 67P. There is one famous exception, a comet catalogued as C/2016 R2, which turned up bizarrely rich in carbon monoxide and poor in water, and which planetary scientists have argued about ever since. But it is the exception that everyone points to precisely because it is alone. And it held for 2I/Borisov, the interstellar visitor of 2019. That was the finding that made everyone comfortable. An object from another star, and it looked like ours. So when the James Webb Space Telescope turned its instruments toward 3I/Atlas on the 6th of August 2025, the expectation was clear. This object had come from an alien system, yes. It would have quirks, certainly. But it would be a comet, and comets are made of water, and the spectrum would show water first with carbon dioxide trailing behind. The observation lasted 18 minutes. 18 minutes to tear a hole in the story. The instrument was called NIRSpec, the Near-Infrared Spectrograph, operating in a mode that makes it not just a spectrograph but a kind of chemical camera. It does not simply record the light of the whole object smeared into one spectrum. It divides the field of view into a grid and takes a full spectrum at every cell of that grid, producing a 3-dimensional block of data, 2 dimensions of sky, 1 of wavelength. You can slice it by color and see exactly where in the cloud each molecule lives. You can watch the shape of a comet's breath. Webb pointed at 3I/Atlas when it was still 3.32 astronomical units from the Sun, well outside the orbit of Mars, more than 3 times Earth's distance from our star, in a place where the sunlight is only about 1/10 as intense as it is here. Cold country. It gathered light across wavelengths from 0.6 to 5.3 micrometers, the range where molecules sing. That word sing is not a decoration. It is close to literal, and it is the reason we can do any of this at all. Molecules are not rigid objects. They are assemblies of atoms held together by electromagnetic bonds that behave, to a decent approximation, like springs. A molecule can vibrate, bonds stretching and compressing, bending, scissoring, can rotate, and here quantum mechanics steps in with its central strangeness. These motions cannot happen at just any energy. They are quantized, restricted to a discrete ladder of allowed states. To climb from one rung to the next, the molecule must absorb a photon of exactly the right energy, which means exactly the right wavelength, which means exactly the right color. Every molecule has its own ladder, set by the masses of its atoms and the stiffness of its bonds. Every molecule therefore absorbs and emits at its own precise set of wavelengths, and no other molecule's pattern is quite the same. Carbon dioxide has an intensely strong vibrational transition near 4.3 micrometers. Water has one near 2.7. Carbon monoxide near 4.7. These are fingerprints. They are not similar to fingerprints. They are better than fingerprints because they are set by fundamental physical constants and are identical for a molecule in a laboratory in Baltimore and a molecule in a cloud of gas orbiting a star in another galaxy. So when a comet's coma is bathed in sunlight, its molecules absorb solar photons at their characteristic wavelengths, get kicked up the ladder, and then fall back down, re-emitting light at those same wavelengths in all directions. The process is called fluorescence. The comet glows in a pattern of specific colors, and that pattern is a readout of exactly which molecules are present and, from the brightness of each feature, roughly how many. This is how humanity performs chemistry on objects it will never touch. We are not sampling 3I/Atlas. We are reading the light it throws away. The spectrum came down. And the first thing anyone would have noticed before any careful analysis, before any modeling at a glance, was that the feature at 4.3 micrometers was enormous. Carbon dioxide dominated the spectrum. Not competed. Dominated. The water feature at 2.7 micrometers was present. It was there unmistakably, along with signatures of solid water ice, carbon monoxide at 4.7, dust scattering sunlight in a broad hump around 1.2 micrometers, and a tentative detection of carbonyl sulfide, a sulfur-bearing molecule. But the carbon dioxide towered over all of it. The team ran the analysis, modeled the fluorescence, derived production rates, and published a number that would be quoted in every subsequent paper on this object. The ratio of carbon dioxide to water in the coma of 3I/Atlas was 7.6, plus or minus 0.3, not 0.076, not 0.76, 7.6. For every molecule of water coming off this thing, roughly 8 molecules of carbon dioxide. Turn that around and hold it. In the comets of our own solar system, water outnumbers carbon dioxide by something like 3 to 1, 5 to 1, 10 to 1, depending on the comet and its distance. In 3I/Atlas, the relationship was inverted, and inverted hard. Carbon dioxide outnumbered water 8 to 1. If you take the typical solar system comet and the interstellar visitor and put their volatile inventories side by side, they are not variations on a theme. They are different substances. The authors were careful, as good scientists are, to make the comparison fair. Comets do not have fixed ratios. The mix changes with distance from the sun, because the more volatile compounds start evaporating farther out while water waits until it gets closer. So you cannot compare a comet observed at 3 astronomical units to one observed at 1. The team plotted the known trend, the relationship between carbon dioxide abundance and heliocentric distance across the whole studied population of long-period and Jupiter family comets, and placed 3I/Atlas on it. It sat 4.5 standard deviations above the trend line. In the language of statistics, that is not an outlier you shrug at. That is a result that is essentially impossible to get by chance from the same underlying population. Whatever process made the comets of our solar system, this object was not made by it. And it was not a marginal case. Excluding the single strange comet C/2016 R2, the carbon dioxide content of 3I/Atlas was among the highest ever measured in any comet by anyone ever. Independent confirmation arrived almost immediately, which is exactly what you want when a result is startling. In mid-August, the SPHEREx mission, a NASA space telescope launched to survey the whole sky in near-infrared, not remotely designed for comet chasing, turned its wide gaze on 3I/Atlas. It found a large, bright, clearly resolved cloud of carbon dioxide gas spanning several arc minutes on the sky, pouring out at a rate on the order of a trillion molecules every second. And it found something else. An extraordinarily strong absorption signature of solid water ice, meaning the comet was throwing out not just gas but a huge population of icy grains, tiny frozen particles lofted off the nucleus and drifting outward in the coma. There was one more detail in the Webb data, easy to miss and quietly bizarre. The outgassing was asymmetric, enhanced on the sunward side. Most of the gas was coming off the hemisphere facing the sun and streaming toward it, against the direction of the solar wind, before eventually being swept back. And the dust was doing something similar, producing a coma that leaned toward the sun rather than away from it. To an observer with a small telescope, this object at times appeared to have an anti-tail, a plume pointing the wrong way, toward the star it was falling into. Anti-tails have perfectly good explanations. They are usually a trick of perspective, an illusion produced when Earth passes through the plane of a comet's orbit and we see a fan of heavy, slow-moving dust nearly edge-on. But combined with everything else, it added to the growing sense among the people watching this object that its ordinary features were assembling into a distinctly extraordinary whole. The carbon dioxide number was the headline, but the headline was not the story. The story was the question that the number immediately raised, and that question is one of the deepest in planetary science. What kind of place makes something like this? There are only a handful of ways to build an object that is 8 parts carbon dioxide to 1 part water, and each of them says something remarkable about the world that made it. The teams working on 3I/Atlas laid out the possibilities carefully, and the debate that followed is a superb example of how science actually proceeds when the data refuse to cooperate. The first possibility is the simplest. The object is exactly what it appears to be. Its nucleus really is intrinsically loaded with carbon dioxide, in a proportion no solar system comet has ever shown, because it formed in a region of its home disk where carbon dioxide ice was abundant and water ice was not. At first that sounds impossible, because water is the most abundant ice in the universe. Hydrogen and oxygen are the first and third most common reactive elements in existence. Water forms readily on the surfaces of cold dust grains in molecular clouds, and it is everywhere. You do not easily build a body starved of water. But you can, under specific conditions, build a body enriched in carbon dioxide relative to water, and the mechanism is a matter of where you sit relative to those nested snow lines. If a body assembles in the region between the water snow line and the carbon dioxide snow line, it will be water-rich. If it assembles just beyond the carbon dioxide snow line, in a zone where the disk is actively concentrating carbon dioxide ice, and if water in that region has already been locked up into larger bodies farther in, then the balance shifts. Disks are not static. Dust grains drift inward. Ices sublimate at one boundary and recondense at another, a process planetary scientists call the cold finger effect, which can pile up specific compounds in narrow bands at their respective snow lines like driftwood on a beach. So one answer is 3I/Atlas formed at the carbon dioxide snow line of its home system, in a spot where that particular compound was locally concentrated. Which is to say that this object is not a random sample of another solar system. It is a sample from a very specific address in that solar system, an address we can identify by chemistry without ever having seen the star. The second possibility is stranger and, in some ways, more beautiful. It is that the carbon dioxide was not deposited but manufactured, made in place slowly over immense time by radiation. Here is the process. Take a lump of dirty ice. Water, carbon monoxide, methane, simple organics, all frozen together in a matrix. Now expose it to ionizing radiation for a very long time. Ultraviolet photons, cosmic rays, the relativistic nuclei that scream through the galaxy at nearly the speed of light. Each strike breaks bonds, ionizes molecules, and creates chemically aggressive fragments called radicals that were not there before. Those fragments recombine into new compounds. Run this in a laboratory on Earth, and it has been run many times in vacuum chambers at Leiden and Catania and NASA Goddard, and the chemistry proceeds in a predictable direction. Carbon monoxide plus a liberated oxygen atom gives carbon dioxide. Methane oxidizes. Simple molecules polymerize into complex refractory organic residues. Given enough dose, an ice that started water-dominated becomes progressively enriched in carbon dioxide, because carbon dioxide is one of the stable endpoints, a chemical sink that things fall into and do not easily leave. That is what a very old, very exposed body should look like. And if this second explanation is right, then the carbon dioxide excess is not a birth certificate at all. It is a suntan. It is the accumulated record of billions of years spent bathing in the radiation field of the galaxy, drifting through interstellar space with no atmosphere, no magnetic shield, and no star to hide behind, being slowly rewritten atom by atom. The Webb team stated it plainly. Their observations were consistent with a nucleus that is intrinsically rich in carbon dioxide, which may indicate that 3I/Atlas contains ices that were exposed to higher levels of radiation than solar system comets, or that it formed close to the carbon dioxide ice line. Either way, the conclusion is the same in the only sense that matters. This object had a history our comets have not had. And there is a third possibility, subtler than either, which turned out to matter enormously as the encounter progressed. That we were not seeing the object at all. We were seeing its skin. Consider what happens to a comet nucleus that has spent an unimaginable length of time in deep space. The outermost layer takes the full brunt of everything: radiation, cosmic rays, micrometeoroid impacts, the slow leak of the most volatile compounds into vacuum. Over billions of years, that outer layer becomes a processed crust, depleted of the most fragile ices, enriched in radiation products, chemically distinct from the pristine material sealed beneath. Now bring that object into a star system. The sun warms the crust first. The first gases you see are the gases from the outermost layer, which is to say, from the least representative part of the whole. It is like judging a loaf of bread by its burnt crust, or more precisely, like reading the cover of a book that has been left out in the weather for 10,000 years and concluding you know the contents. This mattered because 3I/Atlas was observed early, far out, when only the most volatile surface material was active. And it set up the single most illuminating test of the entire encounter. If this third explanation were correct, then the chemistry should change as the object came closer. Heat should penetrate deeper. The crust should be stripped. And what came out later from below should look different, perhaps more normal, than what came off first. That prediction was testable. And in due course, it would be tested in the most direct way possible by simply waiting. But before we get to what the object exhaled at perihelion, we have to deal with the metals. Because while the carbon dioxide was strange in a way that stretched the model, the metals were strange in a way that seemed, for a while, to violate simple thermodynamics. The problem with metal in a comet is that comets are not supposed to have any metal you can see. They have plenty of metal in solid form. Cometary dust is loaded with silicates, iron-nickel grains, sulfides, the same refractory mineral inventory that built the rocky planets. That is not in question and never was. The problem is a different one: gaseous atomic metal. Free-flying individual atoms of iron and nickel, drifting in a comet's coma, glowing with their own characteristic emission lines. To get an atom of nickel or iron out of a solid grain and into the vapor phase, you have to heat it enormously. Nickel boils at about 3000 Kelvin. Even the sublimation of nickel-bearing minerals into vapor requires temperatures around 1300 to 1700 Kelvin, the conditions inside a foundry or on the surface of a planet whose year lasts 88 days. Comets that dive close to the sun, the so-called sun-grazers, do reach such temperatures and do show metal vapor in their spectra. That is expected. That is fine. 3I/Atlas was not a sun-grazer. When high-resolution spectroscopy first revealed atomic nickel in its coma, the object was several astronomical units from the sun, in an environment where the equilibrium temperature of a dark surface is somewhere around 150 Kelvin. That is roughly 180 degrees below zero on the Fahrenheit scale. It is the temperature of a deep cryogenic freezer. Nickel does not evaporate in a freezer. It does not come close. The gap between the temperature required and the temperature available was not a factor of 2. It was a factor of 10, in a process that depends on temperature exponentially. In terms of the physics of sublimation, that gap is not a discrepancy. It is an absurdity. And yet the nickel was there. The emission lines were unambiguous, measured with the ultraviolet and visual Echelle spectrograph on the Very Large Telescope in Chile, an instrument capable of splitting light finely enough to resolve individual atomic transitions and measure their strengths with precision. Then came the detail that turned a puzzle into a genuine anomaly. In the earliest observations, the nickel was present, and the iron was not. That should not be possible either, and for a completely different reason. Iron and nickel are chemical siblings. They sit next to each other on the periodic table, they behave similarly, they condense together out of stellar material, and in every sample of primitive solar system material we possess, meteorites, cometary dust returned by the Stardust mission, the grains measured by Rosetta at Comet 67P, They occur together in a stable proportion, with iron outnumbering nickel by roughly 18-1. That ratio is not a local accident. It is set by nucleosynthesis, by the way stars forge elements in their cores and scatter them at their deaths. It is close to universal. 3I/Atlas was showing nickel vapor with no detectable iron vapor at all. An extreme abundance ratio, as one team put it. Something was separating two elements that nature does not separate. Now, a version of this had been seen before. In 2021, a group working with the Very Large Telescope announced a genuinely shocking result. Nickel and iron vapor in the comas of ordinary solar system comets, far from the Sun, where no such vapor should exist. It had apparently been sitting in archival spectra for decades, unnoticed, because nobody thought to look for lines that could not possibly be there. And in the very same issue of the journal, a separate team reported the same phenomenon in the interstellar comet 2I/Borisov, which showed a strikingly high nickel-to-iron ratio of its own. So this was not unprecedented. It was, however, unexplained, and 3I/Atlas pushed it further than anything before it. The leading hypothesis is one of the most delightful pieces of chemistry in modern astronomy, and it connects the outer solar system to a factory in Victorian England. In 1890, a German-born chemist working in Britain named Ludwig Mond was investigating why the nickel valves in his industrial plant were corroding in the presence of carbon monoxide. What he discovered was that nickel metal and carbon monoxide gas react together at remarkably low temperatures to form a compound called nickel tetracarbonyl, a single nickel atom bonded to 4 carbon monoxide molecules. And nickel tetracarbonyl has a property that makes it almost unique among metal compounds. It is a volatile liquid that boils at just 43 degrees Celsius, barely above body temperature, a metal walking around as a gas. Mond realized what he had. Heat the compound further and it decomposes, dropping out pure nickel and releasing the carbon monoxide to be used again. He had found a way to pick nickel out of impure or carry it away as vapor, and set it down again in a state of extraordinary purity. The Mond process is still used industrially today, more than a century later. It is how a substantial fraction of the world's refined nickel is made. The key point, for our purposes, is selectivity. Nickel forms this carbonyl compound readily under mild conditions. Iron is far more reluctant. Iron pentacarbonyl exists, but forms much less easily, and requires higher pressures and temperatures. If you have a mixture of iron and nickel and you expose it to carbon monoxide gas under gentle conditions, the nickel walks away and the iron stays behind. Now look at a comet. Carbon monoxide, abundant. Metallic nickel and iron in the dust, present. Temperatures far below anything that could evaporate solid metal. Yes, and what comes off is nickel without iron. The chemistry that Ludwig Mond stumbled into while investigating a corrosion problem in a factory appears to be running, unattended, on the surfaces of frozen bodies drifting between the stars. Molecules like nickel tetracarbonyl or related organometallic complexes may be forming in the ice, sublimating at cometary temperatures, and then being broken apart by sunlight in the coma, releasing free nickel atoms that glow in our spectrographs. The metal is not being boiled out. It is being carried out, wrapped in carbon monoxide, by a low-temperature chemical shuttle service. That is the hypothesis. It is not proven. Nobody has directly detected nickel tetracarbonyl in a comet, and its lifetime against solar ultraviolet radiation is short. There are competing ideas that the nickel arrives already in some volatile molecular form inherited from the prestellar cloud, or that it is bound in exceptionally fine grains from which it can be liberated more easily than bulk metal. But whichever mechanism is right, 3I/Atlas did not merely repeat the phenomenon. It amplified it beyond anything previously recorded. As 3I/Atlas fell inward, the metals told a story with a shape to it. A beginning, a turn, and an ending that was somehow more disturbing than the anomaly it resolved. In the beginning, as we have seen, there was nickel and no iron. Then, as the object closed on the sun and the temperature of its surface climbed, iron appeared. Faint at first, then unmistakable. The two elements were both there, and the ratio between them began to shift, moving steadily toward the value seen in ordinary comets. By the time astronomers observed the object after perihelion, using the same high-resolution spectrograph on the Very Large Telescope across heliocentric distances from under 2 astronomical units back out to more than 4, the nickel-to-iron ratio in the coma of 3I/Atlas had become indistinguishable from that measured in solar system comets and in 2I/Borisov. That, on its face, is a deflating result. The great metallic anomaly evaporated. As the object warmed, conventional processes took over, actual thermal liberation of metal from grains, and it began behaving like everyone else. The strangeness had been a temperature effect, a signature of the low-energy chemical pathway dominating while it was cold and being drowned out by ordinary physics once it got warm. Except for one number which the same team highlighted and which reframes the whole thing. The total production rate of nickel and iron atoms from 3I/Atlas, not the ratio between them, but the absolute quantity of metal vapor streaming off this object, was at least an order of magnitude larger than that of any other comet ever measured. 10 times. This object was shedding metallic atoms into space at a rate more than 10 times greater than any comet in our solar system, than any comet in the historical record, than 2I/Borisov. So the resolution of the anomaly did not remove the strangeness. It relocated it. The proportions turned out to be normal, the scale did not. And that points somewhere specific. Not to exotic chemistry but to abundance. A body that outgasses 10 times more metal than any comparable object is most simply explained as a body that contains far more accessible metal in the first place, distributed in a form, perhaps very fine grains, perhaps a more thoroughly mixed matrix, from which it escapes far more readily. Which raises an uncomfortable arithmetic problem, and we will come back to it, because it sits at the heart of one of the loudest scientific arguments of the decade. Meanwhile, another anomaly had been building in parallel, and it concerned the most ordinary substance in the universe. Water sublimates efficiently only when a comet gets within roughly 3 astronomical units of the Sun. That is the classic threshold, taught in every planetary science course. Outside it, water ice is essentially inert. Whatever activity you see is being driven by more volatile compounds like carbon monoxide and carbon dioxide. Inside it, water takes over and the comet comes alive. 3I/Atlas was producing water far outside that boundary. The SWIFT satellite, watching in the ultraviolet, detected the hydroxyl radical, a fragment produced when sunlight breaks a water molecule apart, while the object was still well beyond 3 astronomical units. Webb saw water gas at 3.32. SPHEREx saw an enormous quantity of solid water ice in the coma. The explanation is elegant, and it ties directly to that water ice signature. The nucleus was not sublimating water directly. It was ejecting water ice, throwing off vast numbers of tiny frozen grains, lifted from the surface by the pressure of carbon dioxide and carbon monoxide venting from below. Those grains, once free of the nucleus and drifting in the coma, present an enormous total surface area to sunlight. A single kilometer-scale nucleus has a certain amount of surface. Break that same mass into micron-sized particles and the surface area increases by a factor of millions. Tiny grains also warm up faster and more completely than a large body, which conducts heat away into its cold interior. So the water was sublimating, just not from the comet. It was sublimating from a cloud of ice crystals surrounding the comet, a halo of miniature comets, each one evaporating in the sunlight far more efficiently than the parent body ever could. The engine driving all of this was carbon dioxide. That is the crucial inversion. In an ordinary comet, water is the engine and everything else is along for the ride. In 3I/Atlas, carbon dioxide was the engine and water was cargo, physically carried off the nucleus as solid grains by the pressure of escaping carbon dioxide, then evaporating secondhand. The hierarchy of a comet had been turned upside down. And this is where the prediction from earlier gets its answer, and where the story rewards patience. 3I/Atlas reached perihelion on the 29th of October, 2025, at roughly 1.36 astronomical units from the Sun, inside the orbit of Mars, though never anywhere near Earth. For weeks around that date, it was nearly behind the Sun as seen from our planet, hidden in the glare, unobservable from the ground. Astronomers had to sit through the closest, most dramatic phase of the encounter without being able to look. It is difficult to convey how frustrating that is. The one moment you most want to watch is the one moment the geometry forbids. But spacecraft do not all live at Earth. Mars orbiters positioned very differently in space could see it. Solar observatories designed to stare near the sun could see it. And when 3I/Atlas emerged from behind the glare in the closing weeks of 2025, the world's telescopes were waiting. What they found was that the object had not merely survived. It had woken up. Post-perihelion measurements told a substantially different chemical story. The ratio of carbon dioxide to water, which had been an outrageous 7.6 out at 3.32 astronomical units inbound, had dropped considerably by the time the object was back out at 2.4 astronomical units. Carbon monoxide relative to water had risen slightly, measured at 2.33 with high precision. Those numbers are still extraordinary. A comet with more than twice as much carbon monoxide as water is nothing like a normal comet, but they were no longer the same numbers. The composition had changed, which is exactly what the crust hypothesis predicted. SPHEREx reobserved the object in December of 2025 and reported the transformation in detail. Increased post-perihelion activity, refractory dust in the coma, and new gas species appearing that had not been detected before. The combined carbon monoxide and carbon dioxide content relative to water had fallen to 0.78. Still high, still abnormal, but a fraction rather than a multiple. And a new component had emerged and become significant. Organics, complex carbon-bearing molecules, at roughly 14% of the water abundance. The interpretation offered was precise and illuminating. In August, the behavior of 3I/Atlas had been dominated by the emission of large icy dust grains that were still too cold to sublimate anything less volatile than carbon dioxide. By December, the object had spent months inside the solar system's water ice line, and everything was active. Not just the highly volatile surface ices, but the bulk material of the comet itself. In December, the comet was releasing everything it contained. We had, in effect, drilled into it using the sun. First, we sampled the weathered outer skin, the layer processed by billions of years of radiation in interstellar space. Then, as solar heating penetrated deeper, we sampled the material beneath, the more pristine interior, sealed away since the object formed. And the interior was still strange. Less flamboyantly strange than the crust, but strange in ways that pointed somewhere very specific and much older. Because while all of this was unfolding, other teams had been working on a completely different kind of measurement. Not what molecules were present, but which versions of them. And that is where the real earthquake was waiting. Isotopes are the closest thing nature has to a signature on a document. Every element is defined by the number of protons in its nucleus. Carbon has 6. Change that and you no longer have carbon. But the number of neutrons can vary, and each variant is an isotope of the same element. Chemically nearly identical, physically slightly different, distinguishable by mass. Carbon-12 has 6 protons and 6 neutrons, and it is the overwhelmingly common form. Carbon-13 has 1 extra neutron and makes up a bit more than 1% of the carbon on Earth. Nitrogen-14 dominates its element. Nitrogen-15 is a rare heavy cousin. Hydrogen has 1 proton and normally no neutrons at all, but add a neutron and you get deuterium heavy hydrogen, which behaves like hydrogen but weighs twice as much. Here is why this matters more than almost anything else in observational astronomy. Chemical processes barely care about isotopes. The electrons that do the bonding are the same. But physical processes care intensely, because mass affects how fast a molecule moves, how easily it evaporates, how tightly it binds, how readily a particular reaction runs at low temperature. Over long stretches of time, these tiny mass-dependent preferences accumulate into measurable enrichments or depletions. The resulting isotopic ratios are a permanent record of the physical conditions under which the material assembled: temperature, radiation, density, chemistry, locked in and carried forward, essentially unalterable for the lifetime of the object. An isotopic ratio is a fossil of an environment. And there was a further reason this measurement carried such weight for 3I/Atlas. Isotopic ratios had never been measured in an interstellar object before. Not for ʻOumuamua, which showed no gas at all and vanished in 11 days. Not for 2I/Borisov, which was simply too faint. This measurement requires splitting light into extraordinarily fine slices and then having enough photons in each slice to make a reliable count, and Borisov never delivered enough light. 3I/Atlas was bright enough. For the first time, humanity could measure the isotopic composition of material that formed around another star. The technique deserves a moment because it is a genuinely astonishing feat of engineering. The team at the Very Large Telescope in Chile used the ultraviolet visual Ixchel spectrograph to observe the violet emission band of the cyanide radical CN, a fragment produced in the coma when sunlight destroys hydrogen cyanide molecules and one of the strongest, most easily observed features in any comet. Now, the CN molecule containing carbon-13 instead of carbon-12 is heavier. A heavier molecule vibrates and rotates at slightly different frequencies, so its emission lines sit at slightly different wavelengths than those of the ordinary version. Very slightly. The shift is a fraction of an angstrom, a difference in wavelength of a few parts in 10,000. To measure the isotopic ratio, you must resolve those shifted lines as separate features, identify them among thousands of other lines in a crowded spectrum, model the fluorescence physics to know how bright each version ought to be, and then compare. You are counting individual heavy atoms in a wisp of gas around an object hundreds of millions of kilometers away, by reading the color of light so precisely that you can tell the difference one extra neutron makes to the vibration of a molecule. The measurement came back, and it did not match anything in our solar system. The ratio of nitrogen-14 to nitrogen-15 in 3I/Atlas was measured at approximately 343. In comets of our solar system, that ratio is remarkably consistent, sitting near 150 across essentially the entire population, whether measured in cyanide, hydrogen cyanide, or ammonia fragments, whether the comet comes from the Kuiper belt or the Oort cloud. Near 150 always. It is one of the most stable diagnostic numbers in cometary science, and one of its long-standing puzzles. Our comets are strongly enriched in heavy nitrogen compared to the Sun itself, and nobody fully agrees on why. 3I/Atlas came in at more than twice that value. Its nitrogen was far less enriched in the heavy isotope, much closer to the values measured in the raw interstellar medium in cold prestellar cores, and in the outermost regions of protoplanetary disks around other young stars. Nitrogen isotope fractionation is driven largely by ultraviolet radiation. The dominant mechanism is thought to be isotope-selective photodissociation of molecular nitrogen. Ultraviolet light breaks apart the common form of nitrogen gas slightly more efficiently than the rare heavy-bearing form, releasing atoms that get incorporated into ices with a bias toward the heavy isotope. Run that process for a long time and your ices become enriched in nitrogen-15. Our comets show that enrichment strongly. 3I/Atlas showed it weakly. The implication is that this object formed somewhere the ultraviolet radiation field was much gentler, which means far from its star, out in the frigid outer margins of its disk, or in a system whose star produced less ultraviolet light, or both. Then the carbon result arrived, and it did something even more remarkable. It gave us a date. The carbon isotope ratio is a different kind of instrument entirely. Nitrogen isotopes tell you about local conditions, where in a disk something formed under what radiation. Carbon isotopes tell you about the galaxy itself and about when. To understand why, you have to think about where the two carbon isotopes come from, and they come from different places. Carbon-12 is made in the cores of massive stars, in a process called the triple alpha reaction, where 3 helium nuclei fuse into 1 carbon nucleus. Massive stars burn fast. A few million years, a blink, and die as supernovae, scattering their carbon across the galaxy. This is prompt production. Carbon-12 flooded the early universe quickly, as soon as the first generations of massive stars lived and died. Carbon-13 is different. It is produced mainly in lower mass and intermediate mass stars, in a secondary process that requires carbon that already exists to be reprocessed through the CNO cycle and then dredged up to the surface and blown out in stellar winds. Those stars take a long time to reach that stage, hundreds of millions to billions of years. Carbon-13 arrives late. The consequence is one of the cleanest clocks in astrophysics. Early in the history of a galaxy, the interstellar medium is rich in carbon-12 and poor in carbon-13, so the ratio between them is high. As billions of years pass and generation after generation of slower stars finishes its work, carbon-13 accumulates, and the ratio falls. It has been falling steadily throughout the history of the Milky Way. In our own solar system, the carbon-12 to carbon-13 ratio is about 89. That is the value in the Sun, in Earth's crust, in meteorites, in the comets we have measured. It is a snapshot of the galactic chemical composition 4.5 billion years ago, at the moment our sun's birth cloud collapsed, frozen in place ever since, because nothing that has happened in the solar system since then has changed it appreciably. The present-day interstellar medium in our neighborhood sits somewhat lower, around 68, because another 4.5 billion years of stellar recycling has continued to add heavy carbon. Higher ratio means older. That is the rule. Read the carbon and you read the epoch. The Very Large Telescope measurement of cyanide in 3I/Atlas gave a carbon-12 to carbon-13 ratio of about 147, with substantial uncertainty on either side but a clear central value well above ours. And when a separate team analyzed the carbon dioxide and carbon monoxide molecules directly, using infrared spectroscopy, they found ranges of 141 to 191 for carbon dioxide and 123 to 172 for carbon monoxide. Every one of those numbers exceeds the solar system value. Every one exceeds the values found in nearby interstellar clouds. Every one exceeds the values measured in the protoplanetary disks around young stars in our galactic neighborhood today. The material in 3I/Atlas is chemically more primitive than anything in our solar system. Not slightly, not marginally. Its carbon comes from a galaxy that had not yet accumulated the heavy carbon we take for granted. Run that through the models of galactic chemical evolution, the detailed accounting of how each element and isotope has built up over cosmic time as stars are born, live, and die, and you get an epoch. The carbon isotopic composition of 3I/Atlas corresponds to conditions in the Milky Way roughly 10 to 12 billion years ago. Let that number stand for a moment because it is difficult to hold. The universe is about 13.8 billion years old. The Sun and Earth are about 4.6 billion years old. If the carbon in 3I/Atlas was assembled from a galactic reservoir that existed 10 to 12 billion years ago, then this object predates our solar system by 5, 6, perhaps 7 billion years. It was already ancient when the cloud that made our sun was still gas. It was already ancient when Earth was a magma ocean. It was already older than our entire planet twice over, before there was a single living cell anywhere on this world. And it was still going, still falling through the dark, still coherent, still carrying its chemistry unchanged, for a span of time that dwarfs the entire history of life on Earth. 10 to 12 billion years ago, the Milky Way was in the middle of what astronomers call cosmic noon, the era when galaxies formed stars at rates 10 to 20 times higher than today, when the universe blazed with construction, when the great structural components of our galaxy were being laid down. The Milky Way then did not look like the elegant spiral in the posters. It was smaller, more chaotic, more violent, still swallowing dwarf galaxies whole, still assembling. 3I/Atlas is a relic of that construction site. And somewhere in that turbulence, around some star we can no longer identify, a modest lump of ice and dust came together, and then, for reasons we can only guess at, was thrown away. But the carbon was not even the most extreme measurement. That distinction belongs to hydrogen, and it arrived in 2026, and it is the number that made the loudest noise. Deuterium is heavy hydrogen. 1 proton, 1 neutron, twice the mass of ordinary hydrogen and otherwise almost the same. It has a peculiar and precious property. Essentially, all the deuterium that exists in the universe was manufactured in the first few minutes after the Big Bang, in the brief window when the entire cosmos was hot and dense enough to fuse nuclei. None has been made since in any significant quantity. Stars destroy deuterium rather than create it. The universe has a finite, slowly dwindling supply, minted once, at the beginning. The ratio of deuterium to ordinary hydrogen, written D/H, is one of the most closely watched numbers in planetary science, and the reason is deeply personal to us. Earth's oceans have a specific D/H value, roughly 1 deuterium atom for every 6,400 hydrogen atoms, about 0.016%. That number is a fingerprint, and it has been used for decades to attack one of the oldest questions in planetary science. Where did Earth's water come from? Earth formed inside the water snowline in the hot inner disk. Should have formed dry, and yet more than 2/3 of its surface is ocean. The leading explanations involve delivery, water brought in from beyond the snowline by comets or by water-bearing asteroids, arriving after the planet had cooled. And the way you test that idea is by measuring the D/H ratio in candidate deliverers and seeing which one matches the C. The results have been a long, humbling saga. Comets from the Oort cloud tend to show D/H roughly twice Earth's value, too heavy. Some Jupiter family comets come closer. The Herschel Space Observatory found one, Comet Hartley 2, with a value close to terrestrial, which caused enormous excitement. Rosetta then measured Comet 67P and found a value about 3 times Earth's, which caused enormous disappointment. Carbonaceous meteorites, on the other hand, match Earth's oceans quite well, which is why the current consensus leans toward asteroids as the primary source of our water, with comets contributing a minority share. All of that is a range. All of those measurements across dozens of bodies across the whole solar system fall between roughly 1 and 3 times Earth's ocean value, a factor of a few spread across everything humanity has ever sampled. In 2026, the isotopic measurement of water in 3I/Atlas was published. Its D/H ratio was 0.98%, with an uncertainty of 0.06%. Convert that, about 1 deuterium atom for every 100 hydrogen atoms. Compare it to Earth's oceans at 0.016%. Compare it to the most deuterium-rich comet in our solar system at roughly 0.05%. 3I/Atlas is enriched in heavy hydrogen by more than an order of magnitude beyond any comet ever measured. 10 times, at minimum, outside the entire range of everything in our solar system. This is not a subtle statistical excess or a marginal detection at the edge of instrumental capability. It is a number in a different regime, and it points with unusual precision to a single conclusion. Deuterium enrichment in water is driven by a well-understood set of low-temperature chemical reactions. In extremely cold gas, ion-molecule exchange reactions preferentially load deuterium into molecules, because the deuterated versions sit at slightly lower energy and the reverse reactions require energy the environment simply does not have. The colder it is, the more one-way the traffic becomes, and the higher the deuterium enrichment climbs. This process is temperature-sensitive in a steep, nonlinear way, which makes it a superb thermometer. Run the chemistry backward from a D/H of nearly 1%, and you get a formation temperature at or below 30 Kelvin. 30 Kelvin is minus 243 degrees Celsius, about minus 406 degrees Fahrenheit. It is roughly the temperature of the outer solar system beyond Neptune, out in the Kuiper belt. It is the temperature of a dark, dense prestellar core, a cloud that has not yet lit its star. The paper announcing the results stated its conclusion in a single sentence that will be quoted for a long time. The isotopic composition of 3I/Atlas is unlike any solar system body and indicates formation at temperatures at or below 30 Kelvin in a relatively metal-poor environment. 2 claims from one measurement, both independently supported by the carbon and nitrogen data from other teams using other instruments. Extremely cold. Metal-poor. Metal-poor is worth translating because astronomers use the word metal in a way that would horrify a chemist. To an astronomer, a metal is any element heavier than helium, including carbon, oxygen, and nitrogen. Metallicity means the fraction of a star's material that is not hydrogen or helium. And metallicity is, like the carbon isotope ratio, a clock. The early universe contained essentially nothing but hydrogen and helium, and every heavier atom in existence was forged inside stars and released when they died. Each generation of stars enriches the gas for the next. Old stars are metal-poor. Young stars are metal-rich. So when 4 independent isotopic measurements, deuterium in water, carbon-13 in carbon dioxide, carbon-13 in carbon monoxide, carbon-13 and nitrogen-15 in cyanide, all converge on the same conclusion. The conclusion is not a hypothesis anymore. It is a finding. 3I/Atlas formed around an old metal-poor star in the frigid outer reaches of that star's disk, at a time when the Milky Way was young. And every piece of that conclusion was reached without ever knowing which star. Without a photograph. Without a name. By reading light. There is one more line of evidence, and it comes not from chemistry but from motion, and it agrees. Every star in the Milky Way is moving. The galaxy is not a rigid pinwheel. It is a swarm, and the stars within it are sorted into populations by how they move. The thin disk where our sun lives is a flattened, orderly layer of relatively young, metal-rich stars all circling the galactic center in roughly the same plane at roughly the same speed, like cars on a highway. Above and below it lies the thick disk, an older, puffier, more dispersed population of stars that formed earlier, move faster relative to their neighbors, and swing above and below the plane on tilted orbits. Beyond that lies the halo, the oldest population of all, on wild, plunging, randomly oriented paths. The rule is simple and powerful. The faster a star moves relative to the local average, the older it probably is, because velocity dispersion increases over time. Stars get scattered by encounters with giant molecular clouds, by spiral arms, by the galactic bar. A slow gravitational stirring that heats the population. A star born yesterday moves with the crowd. A star born 10 billion years ago has been kicked around for 10 billion years and moves like it. Interstellar objects inherit the motion of the star that ejected them. When 3I/Atlas is stripped of the sun's influence and its velocity computed relative to the local standard of rest, the average motion of material in our galactic neighborhood, the number is large. Something on the order of 60 kilometers per second. That is roughly 134,000 miles per hour relative to the local flow. Fast enough to cross the continental United States in about a minute, fast enough to travel from New York to London in under 2 minutes. That velocity places 3I/Atlas firmly in the kinematic population of the thick disk, the old stars. Statistical analyses published in 2025 concluded it was very likely an object from that ancient population, possibly the oldest comet ever observed, with age estimates running from 7 billion years to more than 10. And it came in from the direction of Sagittarius, the constellation that lies toward the center of our galaxy. Now put the two independent lines together because this is the part that makes the case airtight. Kinematics said, old, thick disk population. Isotopic chemistry, measured by different people with different telescopes using entirely different physics sensitive to entirely different things, said old metal pore formed when the galaxy was young. Neither measurement depends on the other. Neither could have influenced the other. And they agree. That is what a robust scientific result looks like. Not one dramatic finding, but multiple unrelated methods converging on the same answer from different directions. So we can now write the biography of an object no human eye will ever resolve as anything more than a smudge. Somewhere in the Milky Way more than 10 billion years ago, when the galaxy was a smaller and more turbulent place, a star formed out of gas that had been enriched by only a few generations of stellar deaths. That star was poorer in heavy elements than our sun. Around it spun a disk of gas and dust, and in the frozen outer margins of that disk, at temperatures below 30 Kelvin, far from the star's warmth and shielded from its ultraviolet light, grains of dust began to stick together. Water ice condensed onto them, loaded with deuterium by the slow one-way chemistry of the extreme cold. Carbon dioxide accumulated. Carbon monoxide froze on. Metals in abundance were mixed into the matrix. Organic molecules assembled on the grain surfaces. Over some span of time we cannot measure, those grains built themselves into a body. Perhaps a few hundred meters across, perhaps several kilometers, a dark and frozen lump indistinguishable from a billion others in that system. And then something threw it away. That part is not mysterious. It is routine. Every planetary system ejects a large fraction of its small bodies. A giant planet forming in the outer disk perturbs the leftover debris around it, and much of that debris is flung outward on hyperbolic paths, gone forever. Our own solar system did this on an enormous scale during its youth. The Oort cloud we retain is only the material that was thrown hard enough to leave the inner system but not quite hard enough to escape entirely. The estimates suggest that for every object our sun kept in that distant shell, it lost many more to interstellar space. So the ejection of 3I/Atlas was not a special event. It was garbage disposal, the ordinary byproduct of a solar system settling into its final architecture, and it happened billions of years before Earth existed. What happened next is where the imagination fails. The object entered interstellar space and began to drift. It fell around the galactic center again and again on an orbit of its own, taking something like 200 million years for each lap. It rose above the galactic plane and sank back through it, passed through spiral arms. It passed through the expanding remnants of supernovae. It was bathed continuously in cosmic rays, its outer layers slowly cooked by radiation into the carbon dioxide-rich crust that Webb would eventually detect. Perhaps it drifted near other stars, close enough for their light to warm it faintly, before falling away again into the dark. Meanwhile, back in a quiet region of the thin disk, the cloud that would become our sun collapsed. Earth accreted. The moon was torn out of it. Oceans condensed. Single cells appeared, then multiplied, then complexified. Continents drifted. Ice ages came and went. Dinosaurs ruled for 160 million years and were erased in an afternoon. Mammals rose. A branch of primates in East Africa stood upright, and some of their descendants began to look up and wonder about the lights. Through all of it, this object was in transit. Then, at some point in the recent geological past, its slow galactic wandering happened to bring it into the vicinity of a modest yellow star in the Orion Arm. Fell in, gathering speed. It crossed the outer solar system, then the orbit of Neptune, then Uranus, then Saturn. And on the 1st of July 2025, at a distance beyond Jupiter, a half-meter robotic telescope in the Chilean desert, built by a species that had existed for a rounding error of this object's journey, using a technology invented within a single human lifetime, captured a few photons of reflected sunlight and noticed. 10 billion years of silence, and we caught it on the way past. So now we come to the title question, and it deserves a straight answer rather than a dramatic one, because the truth is more interesting than the hype. Are scientists rewriting the laws of physics because of 3I/Atlas? No. And anyone who tells you otherwise is either confused or selling something. Gravity behaved exactly as Newton and Einstein describe. The object's trajectory was fitted, refined, and predicted with the same equations that steer spacecraft to Saturn. Thermodynamics held. Quantum mechanics held so precisely that we used it to count individual neutrons in molecules hundreds of millions of kilometers away, which is arguably the single most impressive thing in this entire story. No new force was needed. No physical law failed. What failed was something else. What failed was our assumption that our solar system is a representative sample. For 4 centuries, planetary science has been in an unavoidable and rather embarrassing position. It is a science of one. We have studied exactly one solar system from the inside. Every theory of how planets form, how ices are distributed, how volatiles are delivered to habitable worlds, how the architecture of a planetary system emerges from a disk of gas, all of it was constructed from a single example and then, quite naturally, assumed to be general. The exoplanet revolution had already delivered the first hard blow to that assumption. Beginning in the 1990s, as we started finding planets around other stars, the universe made it embarrassingly clear that our arrangement is not the template. We found hot Jupiters, gas giants roasting in orbits closer than Mercury's, which was supposed to be impossible. We found super-Earths, the single most common class of planet in the galaxy, of which our system contains precisely 0. We found compact systems with 7 planets packed inside the orbit of Mercury. We found planets orbiting 2 suns, planets orbiting the corpses of dead stars, planets on wildly elongated orbits. The verdict of 30 years of exoplanet science is that our solar system is somewhat unusual in its architecture. That was blow 1. 3I/Atlas is blow 2, and it lands in a different and deeper place. Architecture is one thing, where the planets ended up is a matter of dynamical history, and dynamics is chaotic, so variety is expected. But composition was supposed to be more universal. Chemistry is chemistry. The elements are the same everywhere. The molecules that form on cold dust grains form the same way in every molecular cloud in every galaxy. That is why 2I/Borisov was so reassuring. It suggested that although planetary systems might be arranged differently, they are built of the same stuff by the same processes into the same kinds of objects. 3I/Atlas says, not necessarily. Here, concretely, is what has to change. The Comet classification scheme must be extended. We had 2 families defined by their reservoirs, both of which turned out to be broadly similar in composition. We now have a confirmed member of a 3rd category, objects from other systems, whose volatile chemistry, isotopic composition, and metal content sit entirely outside the range of both. Textbook comet chemistry is now provincial, a description of what happens in one system rather than a general law. The role of galactic chemical evolution in planetary science has to be taken seriously in a way it never has been. We have implicitly assumed that the raw material of planet formation is roughly constant, that a disk is a disk. It is not. A disk that collapses out of a metal-poor cloud 10 billion years ago starts with a fundamentally different inventory than one that collapses today. Less carbon, less oxygen, less silicon, less iron. Different isotope ratios. Different dust-to-gas ratios which change how quickly solids can grow. The planetary systems that formed in the early Milky Way may have been systematically different from the ones forming now, and since most of the stars in the galaxy are older than the Sun, that means the typical planetary system may be nothing like ours. The chemistry of cold formation environments needs revisiting. A deuterium enrichment of 1% is a strong constraint that our models must now reproduce, along with the coexistence of primitive nitrogen isotopes and extreme carbon dioxide abundance in one body. And the volatile delivery story for habitable planets, the story of how water arrived on Earth, has just become more complicated and more interesting. If interstellar objects carry water this isotopically exotic, and if they are common, then some fraction of the water on any given planet in the galaxy may have been delivered from outside its own system entirely, carrying an isotopic signature from a different star, a different era, a different chemistry. That is what is being rewritten, not the laws, the scope. There is an old and useful distinction here. Physics gives us the rules, but the rules alone do not tell you what actually happened, any more than knowing the rules of chess tells you the history of every game ever played. Between the laws and reality lies contingency, the specific circumstances of specific places at specific times. Planetary science lives in that space. And what 3I/Atlas demonstrated is that the space is far larger, far stranger, and far more varied than our single sample ever suggested. Which brings us to the part of the story where the argument got loud. No account of 3I/Atlas would be honest without addressing the argument that dominated public conversation about it. And that argument centers on one man, one hypothesis, and a question about how science should handle its own outliers. Avi Loeb is a theoretical astrophysicist at Harvard University. He is not a fringe figure by credential. He chaired Harvard's astronomy department, he founded its Black Hole Initiative, he has published hundreds of papers across cosmology and astrophysics, and by any conventional measure he is one of the more accomplished theorists of his generation. Beginning with ʻOumuamua in 2018, Loeb has argued consistently and publicly that when an interstellar object displays properties we cannot explain with natural processes, the possibility that it is artificial, a manufactured product of another civilization, deserves to be tested seriously rather than dismissed reflexively. With ʻOumuamua, his argument had a specific technical basis. The object accelerated without visible outgassing, and he proposed that radiation pressure from sunlight acting on a very thin, very large, very lightweight structure could account for it. A light sail, possibly derelict, possibly not. When 3I/Atlas was discovered, Loeb turned the same lens on it, and he published prolifically, dozens of essays and papers week after week, cataloging every anomaly and asking, each time, whether the natural explanation was really adequate. He drew attention to the fact that its trajectory lay unusually close to the plane of the planets, and that it passed relatively near Mars, Venus, and Jupiter in a way he calculated to be improbable by chance. He noted the sunward-facing jet and the anti-tail. He noted the exotic chemistry, the nickel without iron, the extraordinary metal production. He raised the non-gravitational acceleration measured after perihelion. He proposed observational tests and argued for spacecraft response. And the mainstream astronomical community reacted with a mixture of irritation, exasperation, and in some quarters genuine anger. Statements were issued. Colleagues wrote publicly that the alien framing was damaging to the field, that it distorted media coverage, that every one of the anomalies had a natural explanation already on the table, and that responding to each new claim was consuming time better spent on the actual science. So who was right? On the specific question, the evidence is clear and it does not favor the artificial hypothesis. Almost every individual anomaly that was cited has, over 18 months, acquired a solid natural explanation. The nickel-to-iron ratio normalized as the object warmed, exactly as low-temperature chemistry predicts. The anti-tail is a well-known projection effect. The non-gravitational acceleration is precisely what you expect from an actively outgassing comet, and 3I/Atlas was outgassing prodigiously. The effect was measured and modeled and found consistent with cometary jetting. The trajectory alignment, examined statistically, is well within what chance produces given the geometry of how such objects are discovered. We find them where our surveys look, and our surveys look near the ecliptic. And most decisively, the isotopic measurements settled the origin question in a way no other data could. Deuterium enrichment of 1%, elevated carbon-12 to carbon-13, elevated nitrogen-14 to nitrogen-15. These are signatures of low-temperature chemistry in an old metal-poor environment. They are not the signatures of manufacture. Nothing built by anyone produces a deuterium enrichment characteristic of 30 Kelvin ion molecule chemistry as a byproduct. The isotopes say this object condensed out of a cold cloud, and cold clouds are not factories. 3I/Atlas is a comet, an extraordinary, ancient, chemically alien comet, but a comet formed by natural processes in a protoplanetary disk around a star that died or drifted away long ago. And yet, the more interesting question is not whether Loeb was right. It is whether the argument was worth having. There is a real case that it was. The alien hypothesis, whatever its merits, functioned as an adversarial stress test. Every claim it made demanded a rigorous natural rebuttal, and producing those rebuttals generated real science, careful statistical analyses of trajectory probabilities, detailed modeling of non-gravitational forces, precise photometry. Several papers exist that would not exist otherwise. A field forced to defend its assumptions examines them more carefully than one left alone. There is also a real case that the public attention, whatever its distortions, was net positive. Millions of people who would never have heard of an interstellar object followed this one. Some fraction of them learned what an eccentricity is, or what a spectrum measures, or why isotope ratios matter. The chemistry in this story is genuinely more astonishing than the alien hypothesis, and a certain number of people arrived for the aliens and stayed for the deuterium. And there is a real case on the other side, which should not be waved away. Extraordinary claims consume attention, and attention is finite. When a credentialed scientist publishes weekly speculation about extraterrestrial technology, the coverage tends to lead with that regardless of the caveats attached. And the working scientists producing the actual measurements find their results reduced to a footnote in someone else's story. Several researchers who did the difficult work on this object expressed exactly that frustration. Both things are true. That is uncomfortable, and it is how these situations usually resolve. But there is one contribution from Loeb that has nothing to do with aliens, that the mainstream has taken seriously, and that constitutes a genuine unsolved problem. It is a piece of arithmetic, and it may be the most legitimately troubling result to come out of this entire encounter. The problem is one of accounting, and it goes like this. We have now detected 3 interstellar objects in roughly 8 years, using survey telescopes with known sensitivity, known sky coverage, and known observing cadence. From that, you can work backward to estimate how many such objects must be drifting through interstellar space to make 3 detections likely. It is the same statistical logic a biologist uses to estimate a population from a tagging study, or an epidemiologist uses to estimate infections from a sample. The answer is a number density, how many interstellar objects per cubic parsec of the galaxy, and the numbers that come out are enormous. Estimates have ranged widely, but the general picture is that interstellar space contains something like 10 to the 26th power of these objects per cubic parsec, which works out to a great many trillions of them within a volume the size of our solar system's neighborhood at any given moment. Empty space is, statistically, not empty at all. Now do the mass budget. Each of these objects has a mass. 3I/Atlas in particular was inferred to be relatively large, and if the nucleus is at the upper end of the size estimates, its mass is substantial. Multiply the estimated mass of a typical object by the estimated number density, and you get a total mass of ejected planetary debris per unit volume of the galaxy. Then compare that against the total supply of raw material available. Every atom heavier than helium in the galaxy was made in stars. The total inventory of heavy elements is finite and reasonably well constrained by observations of stellar populations, gas, and dust. And crucially, if these objects come preferentially from old metal-poor stars, as the isotopic evidence strongly suggests, then the available reservoir is smaller still, because metal-poor stars by definition contain fewer heavy elements to build such bodies out of in the first place. The comparison fails. Loeb's calculation, published in 2026, found that the inferred radius and interstellar number density of 3I/Atlas-like objects imply a local mass density larger by orders of magnitude than the available reservoir of heavy elements locked in low metallicity stars. Orders of magnitude. not a discrepancy of 30% that might be absorbed by refined estimates. A factor of hundreds or more. The universe does not fail to balance its books. So one of the inputs is wrong, and the interesting question is which one. Perhaps the size estimate is too large. Measuring the nucleus of an active comet buried inside a glowing coma is notoriously difficult, and if 3I/Atlas is substantially smaller than inferred, the mass problem shrinks dramatically. Perhaps the number density is too high. 3 detections is a tiny sample, and the statistics of small numbers are treacherous. If we have simply been lucky, if the past 8 years happened to catch an unrepresentative cluster, then the true population is smaller. Perhaps the association with metal-poor stars is wrong, or at least too narrow. Perhaps the isotopic signature indicates something about the specific formation region rather than the bulk metallicity of the parent star, in which case the available reservoir is much larger. Or perhaps something in our understanding of how planetary systems eject material is significantly off. Perhaps ejection is far more efficient than we model, or perhaps a class of stellar system we have not properly accounted for is manufacturing these things in bulk. Nobody knows. And that, rather than any speculation about technology, is where the genuine frontier sits. A well-posed quantitative contradiction between two independently estimated quantities is exactly the kind of problem that has historically preceded real advances. The problem is not that we found something we cannot explain. The problem is that the numbers, taken at face value, cannot all be true at once. Meanwhile, while the arguments raged, the object itself was doing something that no interstellar visitor had ever done. It was being watched from another planet. On the 3rd of October 2025, 3I/Atlas passed Mars at a distance of roughly 29 million kilometers, about 18 million miles, or a fifth of the distance between Earth and the Sun. By the standards of interplanetary space, that is close. By the standards of an object that had been traveling for 10 billion years, it was practically a collision. And Mars, as it happens, is the most heavily instrumented planet in the solar system after our own. In orbit around it at that moment were spacecraft from 3 space agencies. NASA's Mars Reconnaissance Orbiter with its remarkable high-rise camera, capable of resolving objects the size of a dining table on the Martian surface. MAVEN, designed to study the escape of the Martian atmosphere. The European Space Agency's Mars Express and the ExoMars Trace Gas Orbiter, and spacecraft from other national programs. On the surface, rovers with cameras designed for geology and atmospheric science. None of these machines was built for this. Not one. They were designed to stare downward at a planet, not outward at a fast-moving speck. Their cameras are optimized for bright, close, slow-moving terrain, not faint, distant, rapidly shifting points of light. Asking HiRISE to photograph a comet is like asking a microscope to take a portrait of a bird in flight. They tried anyway, and this is one of the quiet triumphs of the whole affair, the improvisation of it. Observing campaigns were assembled in weeks rather than years. Spacecraft were commanded into orientations their designers never anticipated. Instruments were pushed past their intended operating envelopes. Engineers who had spent their careers studying Martian dust devils found themselves writing pointing sequences for an interstellar comet. The scientific value of the Mars vantage point was real and specific. From Mars, the object was seen from a completely different angle than from Earth. Combine images from 2 widely separated viewpoints and you get parallax and 3-dimensional structure, the true shape of the coma rather than its projection, the real geometry of the dust fan, better constraints on the size of the nucleus hidden inside. And the Mars orbiters could keep watching through the period when Earth-based telescopes were blinded. Because that blindness was coming, and it was severe. As 3I/Atlas approached perihelion on the 29th of October, it moved into solar conjunction as seen from Earth, sliding behind the glare of the sun, into the one region of sky no ground-based telescope can observe and where even space telescopes cannot point without risking their optics. The timing was cruel in a way that felt almost deliberate. Perihelion is the climax. It is the moment of maximum heating, maximum outgassing, maximum activity, when the interior of the object is most thoroughly exposed and the chemistry is at its most informative. It is the moment a comet tells you the most about itself. And for that moment, from the surface and orbit of Earth, we were blind. This is the sort of frustration that does not make it into press releases. Careers are built on observing windows, and observing windows are set by celestial mechanics, which does not negotiate. Astronomers had known this was coming since July. They had months to plan around it and no way to prevent it. What they did instead was surround the gap. Ground-based observatories pushed as late into October as the geometry allowed, chasing the object lower and lower toward the horizon at twilight. Solar observatories designed to stare at the sun, spacecraft with coronagraphs that blocked the solar disk to study the corona, could see into the region near the sun and looked for the comet there. The Mars fleet contributed its different angle, and amateur astronomers around the world, whose contribution to this field is genuinely enormous and consistently underappreciated, filled gaps in the light curve with observations from backyards and small private observatories, tracking the object's brightness night by night. Then, in November and into December, 3I/Atlas emerged from the glare, and the whole apparatus swung back onto it. It was brighter than expected. Comets are notoriously unpredictable in this respect. The old astronomical saying is that comets are like cats, they have tails and they do exactly what they want. Some fizzle at perihelion. Some disintegrate entirely, as Comet Ison famously did in 2013, evaporating before an audience of millions who had been promised a spectacle. Some brighten far beyond predictions. 3I/Atlas brightened. The December observations showed increased activity relative to the pre-perihelion period, a coma loaded with refractory dust, the durable mineral component that only comes off when the surface is being aggressively eroded, and, as we have seen, an entirely new chemical profile with significant organic content that had not been detectable before. The object had come through its encounter with our star intact and had been comprehensively opened up by it. The sun did for us what no spacecraft could have. It drilled through the crust, vaporized the outer layers, and released the interior for inspection. There was also, in the post-perihelion tracking, a measurable non-gravitational acceleration. The object's path deviated slightly from what pure gravity predicted. This was the datum that generated the loudest speculation, and it is worth being precise about it, because precision is where the drama drains out and the physics remains. Non-gravitational acceleration in comets is neither rare nor mysterious. It was first inferred in the 19th century, quantified in the 20th, and is routinely included in the orbit-fitting software used by every dynamicist on Earth. A comet vents gas. The gas carries momentum. The nucleus recoils. Since the venting is uneven, stronger on the sunlit side, concentrated in active regions, modulated by rotation, the net thrust is small but persistent and pushes the object off a purely gravitational path. For 3I/Atlas, the observed deviation was consistent with the outgassing that had been directly measured by multiple observatories. This was not a case of acceleration without a visible cause, as with ʻOumuamua. This object was demonstrably, spectacularly venting, a carbon dioxide production rate on the order of a trillion molecules per second, plus water, plus carbon monoxide, plus a torrent of dust and metal. Of course, it was being pushed. It would have been far more alarming if it had not been. The rocket equation applied to a comet gives a small number, but small numbers integrated over months of continuous thrust produce measurable trajectory changes. The measurement was, in the end, another confirmation that the object was behaving as a natural comet with an extraordinary composition, which is precisely the summary of this entire story. And by early 2026 it was climbing back out, dimming steadily, its speed slowly bleeding off as it fought its way up the sun's gravity well, though never enough to matter. It had arrived hyperbolic and it would leave hyperbolic. The sun bent its path and slowed it temporarily and could never hold it. Among the molecules detected in the coma, there is a category that deserves separate attention, because it connects this frozen wanderer to the most consequential question anyone can ask about the universe. Webb detected carbonyl sulfide, a molecule of carbon, oxygen, and sulfur. The Very Large Telescope and radio observatories detected hydrogen cyanide, the parent of the cyanide radical used for the isotope measurements. Methanol was found, and in an unusual proportion. The ratio of methanol to hydrogen cyanide in 3I/Atlas was measured to be very high compared with solar system comets. And in December, after perihelion, SPHEREx reported a substantial population of organic gases, at roughly 14% of the water abundance. Those are not exotic laboratory curiosities. They are the standard opening moves of prebiotic chemistry. Hydrogen cyanide is arguably the single most important small molecule in the study of life's origins. It is chemically aggressive, it polymerizes readily, and its reaction networks lead, in laboratory experiments that have been refined for 70 years, to amino acids, to the nucleobases that spell out the genetic code, and to the sugar backbones of RNA. In 1961, Juan Oro showed that a concentrated solution of hydrogen cyanide and ammonia produces adenine, one of the 4 letters of DNA, essentially on its own. Hydrogen cyanide chemistry is now central to the leading scenarios for how the first self-replicating molecules assembled. Carbonyl sulfide is a similarly loaded compound. Sulfur chemistry is essential to biology. The amino acids cysteine and methionine contain it, and iron-sulfur clusters sit at the heart of ancient metabolic enzymes that are thought to trace back to the earliest life. And carbonyl sulfide specifically has been demonstrated in the laboratory to drive the formation of peptide bonds, joining amino acids into chains, which is the step that turns a soup of building blocks into the beginnings of a protein. Methanol is a versatile feedstock that leads to formaldehyde and to sugars through the Formose reaction. So the inventory being carried by this 10-billion-year-old fragment of another star system includes hydrogen cyanide, carbonyl sulfide, methanol, complex organics, and abundant water. That is more or less a starter kit. Now, this must be stated with care, because the space between prebiotic molecules were present and life was involved is enormous and is regularly abused. There is no evidence of biology in 3I/Atlas. None. These molecules form abundantly through ordinary chemistry on the surfaces of cold dust grains, driven by ultraviolet photons and cosmic rays, in molecular clouds throughout the galaxy. They are found in star-forming regions, in comets, in meteorites, in the interstellar medium. Their presence indicates chemistry, not life, but their presence in an object from another star system, formed around a different sun 10 billion years ago in a metal-poor early galaxy, tells us something that we could not otherwise have known, that this chemistry is not a local specialty. The molecular precursors of life assembled themselves in a solar system utterly unlike ours, under a star unlike ours, at a time when the galaxy had barely begun to make heavy elements. The same molecules, not analogs, not equivalents, the same molecules in a body from another world. That is a substantial statement about the universality of the chemical foundation on which life on Earth was built. Whatever happened here 4 billion years ago, it started with a set of ingredients that the galaxy appears to manufacture everywhere, in every era, under a wide range of conditions. This is also where the idea of panspermia comes up, and it deserves a fair and skeptical hearing. Panspermia is the hypothesis that life, or its precursors, is distributed between star systems by natural transport, that microorganisms or organic material can survive ejection from a planet, the long crossing of interstellar space, and arrival at another world. It is an old idea, floated by Anaxagoras, revived by Lord Kelvin, and championed in the 20th century by Fred Hoyle and Chandra Wickramasinghe. Interstellar objects are the transport mechanism the hypothesis requires. Before 2017, that mechanism was purely theoretical. We had no confirmed example of material passing from one star system to another. Now we have 3, and population estimates suggest the galaxy is filled with them. The strong version of panspermia, that living organisms make the crossing, remains extremely difficult. The obstacles are formidable. The violence of ejection, exposure to cosmic radiation for millions or billions of years with no magnetic shielding, near absolute zero temperatures, and finally the problem of arrival, since an object entering an atmosphere at 60 kilometers per second is not gently delivered. Some experiments show that certain bacterial spores and tardigrades survive vacuum, radiation, and extreme cold for years, protected inside rock. Extrapolating that to 10 billion years is a stretch that most researchers are unwilling to make. The weak version, that the chemical precursors of life travel between systems, no longer needs defending. It has been observed. 3I/Atlas is carrying hydrogen cyanide and carbonyl sulfide and organics from another star, right now, through our solar system. Whether or not any of it lands anywhere, the transport is happening, and it has been happening for as long as there have been planetary systems. Which means the galaxy is not a set of isolated chemical experiments running in parallel. It is, in some measure, connected. Material moves. Not efficiently, not quickly, not in quantities that dominate any planet's inventory, but continuously over billions of years in every direction, an endless slow drizzle of debris from every planetary system that has ever formed, passing through every other one. Our own solar system has certainly received such material throughout its history. Objects like 3I/Atlas have been falling through since the beginning, and some fraction of them will have struck the planets. During the early bombardment, when Earth was accumulating its final mass and its oceans, interstellar debris was arriving alongside everything else. The probability that any particular molecule in your body came from another star system is vanishingly small. But the probability that some atoms now on Earth arrived here from outside the solar system, carried by an object like this one, is essentially certain. It is worth dwelling on the journey itself, because the journey is not empty time. It is a process, and it left marks. Interstellar space is often described as a vacuum, and by laboratory standards it is an extraordinarily good one, roughly 1 atom per cubic centimeter in the general diffuse medium, which is emptier than anything we can produce on Earth. But the galaxy is not uniform, and an object crossing it for 10 billion years does not travel through one environment. It travels through many. It passes through the warm, ionized medium, thin gas at thousands of degrees, glowing faintly, passes through cold neutral clouds. It passes, occasionally, through giant molecular clouds, vast complexes of dense, frigid gas where new stars are forming, where the density can be 1,000,000 times higher than the average and where an object would encounter more material in a few thousand years than in the preceding 100 million. It crosses spiral arms, which are not solid structures but density waves, regions of compression where star formation is concentrated and where massive stars live briefly and die violently. And it is exposed, without interruption, to cosmic rays. Cosmic rays are atomic nuclei accelerated to relativistic speeds, mostly by the shock fronts of supernova explosions. They stream through the galaxy in all directions, and they are the single most important agent of chemical change acting on unshielded ice. When a cosmic ray strikes a frozen surface, it does not simply chip material away. It deposits energy along a track through the ice, ionizing molecules, breaking bonds, and creating a cascade of chemically aggressive fragments that then react with one another. Over 10 billion years, the accumulated dose is enormous. Laboratory experiments and theoretical estimates suggest that the outermost layers of an interstellar body, the first meter or so, receive enough radiation to be thoroughly and irreversibly transformed. Volatile molecules are destroyed and recombined. Simple organics polymerize into a dark, refractory, carbon-rich residue, the substance sometimes called organic tholin, which is why comet nuclei and outer solar system bodies are among the darkest objects known, reflecting only a few % of the light that hits them. The most volatile species escape. Carbon dioxide, being a stable endpoint of oxidation chemistry, accumulates. This is the physical basis of the crust hypothesis, and it makes a strong prediction. The outside of an interstellar object should not resemble its inside. The outside is a radiation product. The inside, protected by that very crust, may be nearly pristine, which is precisely what the observations showed. Carbon dioxide dominated outgassing when only the surface was warm. A completely different profile, organics, refractory dust, much lower carbon dioxide relative to water, once solar heating had penetrated deeper. The chemistry of 3I/Atlas changed as it was peeled. But there is a problem lurking here, and it is one of the genuinely unresolved issues in the field. If 10 billion years of cosmic ray exposure and micrometeoroid bombardment and slow sublimation act on a body of this size, should anything volatile survive at all? Estimates of interstellar erosion vary considerably, but the processes are not gentle. Sputtering by impacting particles removes material. Sublimation into vacuum, even at 10 or 20 Kelvin, is not zero over 10 billion years. Extremely volatile species like carbon monoxide have measurable vapor pressures even at those temperatures. Impacts by interstellar dust grains, arriving at tens of kilometers per second, excavate craters and expose fresh material. And yet 3I/Atlas arrived loaded with carbon monoxide, one of the most volatile compounds there is, producing it in quantities more than twice its water output after perihelion. It arrived so volatile rich that it was already actively venting beyond the orbit of Jupiter, where most solar system comets are dormant. Something protected it. The likely answer is the crust itself, that the processed outer layer acts as an insulating and sealing barrier, a lid that keeps the interior cold and prevents volatiles from escaping. It is the same mechanism that lets some solar system comets survive many perihelion passages. The surface builds up a mantle of dust and refractory material that chokes off sublimation from below. But over 10 billion years, with cosmic rays penetrating and impacts excavating, the survival of a substantial volatile inventory is a genuine constraint on models of interstellar erosion, and one that current models do not comfortably satisfy. There is another possibility worth mentioning, and it is speculative but not absurd. Perhaps 3I/Atlas did not spend 10 billion years fully exposed. Perhaps it was ejected relatively recently from a distant reservoir around its parent star, an Oort cloud equivalent, where it had been stored for most of its existence, shielded to some degree, still nominally within its home system. The isotopes date the formation of its material, not the moment of its ejection. A body could form 10 billion years ago, sit in a distant orbit for 9 billion of them, and only then be released, by the death of its star, by a passing stellar encounter, by the slow tug of the galactic tide. That scenario would resolve the erosion problem, and it has an unsettling implication. We may not be able to tell the difference. The chemistry tells us when the material formed. It does not tell us how long the object has been homeless. Either way, the object we observed was not a pristine sample. It was a weathered one, a body that had been through something, that carried the record of that something in its outer layers, and that only revealed its interior when a star it had never met heated it enough to break the seal. We did not just catch a fragment of another solar system. We caught a fragment that had been out in the weather of the galaxy for longer than the Earth has existed, and we watched the sun open it. And what did it actually look like? Here the answer is humbling, and it says something about the limits of even the best remote observation. Nobody ever saw 3I/Atlas. Not really. Every image of it, from Hubble, from Webb, from the Very Large Telescope, from Mars orbit, from every backyard telescope that tracked it, shows a coma, a cloud, a glowing envelope of gas and dust, tens of thousands of kilometers across, entirely opaque to the question of what sits at its center. The nucleus, the actual solid object, was never resolved. Could not be. At those distances, with those instrument resolutions, a body of a few kilometers is far below the size of a single pixel, and it was in any case buried inside its own atmosphere. So everything we say about the physical object is inference from the light of the cloud around it, and the inference is genuinely difficult. Start with color. The reflected sunlight from the coma was measured across the visible and near-infrared, and the object was reported as reddish, redder than the sun, in the range typical of comets and outer solar system bodies, consistent with the presence of that dark, radiation-processed organic material on the grains. This is a real measurement and it carries information. It tells you the dust is not fresh silicate, that it has been chemically cooked, that the surface material is of a type familiar from the outer solar system. Then dust. The behavior of dust in a coma is a rich diagnostic, because dust grains respond to two competing forces: the gravity of the nucleus, which is negligible, and radiation pressure from sunlight, which pushes them away from the sun. The strength of radiation pressure relative to a grain's mass depends on its size. Small grains get pushed hard and stream away quickly into a tail, while large grains barely move and linger near the nucleus, spreading slowly into a broad fan roughly along the orbital path. 3I/Atlas showed the signature of large grains. That is what produced the odd, tail-pour appearance in many images, and what set up the anti-tail geometry. Instead of a long, elegant dust tail streaming away from the sun, this object produced a compact, asymmetric coma with dust concentrated near the nucleus and skewed sunward. The visual signature of heavy particles ejected at low speed and hanging around, combined with a viewing geometry that placed Earth near the plane of the comet's orbit. That large grain dominance is not a trivial detail. It is directly connected to the water story. To lift a large, heavy grain off a nucleus, you need substantial gas drag, which means substantial gas production, which is exactly what the carbon dioxide venting provided. And the largest of those grains, if they contained water ice, are precisely the objects that carried water into the coma to evaporate secondhand. Everything in this object's physics connects back to the same inversion. Carbon dioxide as the driver, everything else as cargo. Polarization measurements were made as well, the degree to which the scattered sunlight from the coma is polarized, which depends sensitively on grain size, shape, porosity, and composition. Comets follow a characteristic polarization curve as a function of the angle between Sun, comet, and Earth, and deviations from that curve indicate unusual dust. Reports on 3I/Atlas suggested it did not sit comfortably on the standard curve. And the James Webb spatial mapping showed the outgassing was not uniform. It was enhanced sunward, consistent with a nucleus where active regions vent when they rotate into sunlight. That is ordinary cometary behavior in principle. But mapping those jets in detail would have required resolution we did not have. So the physical portrait of 3I/Atlas is a rough sketch. A dark, reddish, irregular body of uncertain size, rotating at an uncertain rate, with localized active regions on a surface we never saw, surrounded by unusually large dust grains loaded with water ice, venting carbon dioxide with enough force to lift them. That is the best portrait humanity will ever have of this particular object. It will not improve. There is no going back. This is the deepest argument for missions like Comet Interceptor, and for the surveys that would give us enough warning to launch one. Everything in this story, the extraordinary chemistry, the isotopes, the metals, the age, was derived from light emitted by gas that had already left the object. Not one measurement touched the surface. Not one image showed the nucleus. The single most important physical parameter, its size, remains uncertain by a factor that makes its mass uncertain by 1,000. We read a document without ever seeing the paper it was written on. That we learned as much as we did is remarkable. That we could not learn more is the reason a generation of planetary scientists is now working, urgently, on the problem of how to be ready for the next one. Return, for a moment, to that deuterium number, because it has an implication that reaches all the way down to the water in your glass. The reason planetary scientists have spent decades measuring D/H ratios in comets and asteroids is that they are trying to solve the mystery of Earth's oceans, and the method depends on a specific assumption, that the possible sources of Earth's water are all local. Oort cloud comets, Jupiter family comets, carbonaceous asteroids from the outer belt, different reservoirs, different D/H values, and the job is to find the mixture that reproduces the ocean. That approach implicitly assumes a closed system. All the water in our solar system came from our solar system's disk, which inherited it from our particular molecular cloud, which had one particular D/H value that then got modified in various ways depending on where in the disk the material ended up. 3I/Atlas breaks the closure. If interstellar objects are as common as the population estimates suggest, then every planetary system, including ours, has been receiving foreign material continuously since its formation. Some of that material carries water with a D/H ratio wildly different from anything the local disk produced. In this case, 10 times higher than any local comet. Not a slight variation to be averaged in. A completely different isotopic population. The amount is almost certainly small. Nobody is proposing that Earth's oceans came from interstellar comets. The local sources are far more abundant, and the isotopic match to carbonaceous meteorites is too good to overturn. But small is not zero, and the existence of a foreign component that has never been accounted for adds a genuine uncertainty to a calculation that was already delicate. There is a broader implication too, and it concerns habitability across the galaxy. We are used to thinking of a planetary system as a self-contained accident. Whatever the disk provided, the planets received. Under that view, a planet's chance at being habitable depends entirely on local circumstances, where it formed relative to the snowline, whether a giant planet was positioned to deliver volatiles inward, whether the disk was rich or poor in the relevant elements. But if every system is embedded in a galaxy-wide drizzle of ejected debris from every other system, then the accounting changes. A planetary system born unusually dry could be watered, in part, from outside. A system born in a metal-poor environment could receive organics manufactured in a metal-rich one. Over billions of years, the galaxy performs a slow, inefficient, but relentless redistribution of planetary building material. That is a genuinely new consideration in the study of habitability, and it exists as a serious topic largely because of these three objects and especially the third. There is also a strange kind of consolation buried in the chemistry, because 3I/Atlas is not just an object. It is evidence about a place, and the place is gone. Consider what we know. It formed around a star older and poorer in heavy elements than the Sun. That star may still exist somewhere in the thick disk of the Milky Way, an ancient dim body indistinguishable from millions of others. It may have died long ago. Depending on its mass, it could have swollen into a red giant and shed its outer layers, leaving a white dwarf. If it was more massive, it may have exploded. Whatever planets it had may have been engulfed or scorched or flung free. We cannot identify it. The object's velocity is known, so its trajectory can in principle be traced backward. But over 10 billion years, the galaxy has stirred itself thoroughly. Stars migrate. Orbits are perturbed by molecular clouds and spiral arms and the galactic bar. The backward trace diverges into uselessness after a few tens of millions of years at most. There is no arrow pointing home. So this is a message with a return address that has been erased. All we have is the contents, and the contents describe a world we will never locate. A cold outer disk, dim ultraviolet light, water heavy with deuterium, carbon from an early galaxy, metals in abundance, organics on the grains, and enough gravitational chaos in the system to throw this piece of it out into permanent exile. That is a portrait of a solar system, not ours, reconstructed entirely from the light of a fragment that escaped it 10 billion years after the fact. And here is the part that ought to give anyone pause. That system, whatever it was, is now represented in our records by exactly one object. We know it existed. We know roughly what its outer disk was made of, and roughly how cold it was, and roughly how old its star was. We know essentially nothing else, and we never will. A planetary system's entire biography, reduced to one paragraph, derived from one comet caught by accident for a few months before it left. Multiply that by the hundreds of billions of stars in this galaxy, most of which formed before the sun, most of which had disks, most of which ejected debris. Each one has been dispersing fragments of itself into the dark for billions of years. Each fragment is a paragraph about a world nobody will ever visit. The galaxy is full of these paragraphs. We have now read 3, which brings us to the most consequential fact about the near future of this field. We are about to read a great many more. On a mountain called Cerro Pachón in Chile, the same country, the same clear desert sky that gave us 3I/Atlas, stands an observatory that changes the arithmetic of discovery. It is called the Vera C. Rubin Observatory, named for the American astronomer whose measurements of galactic rotation in the 1970s provided the first compelling evidence for dark matter, and who spent a career being underestimated by a field that has since named its most ambitious survey telescope after her. The Rubin Observatory is built around an 8.4-meter mirror and, crucially, the largest digital camera ever constructed for astronomy. 3.2 gigapixels, roughly the size and weight of a small car, cooled to cryogenic temperatures, capable of photographing a patch of sky 40 times the area of the full moon in a single exposure. Its mission, the legacy survey of space and time, is to photograph the entire visible southern sky every few nights, continuously, for 10 years. Not a targeted survey of selected objects, the whole sky over and over, producing something like 20 terabytes of data every night and generating millions of alerts about anything that changes or moves. For interstellar objects, this is transformative. Every previous detection was a matter of luck. 3I/Atlas was caught by a half-meter telescope built to find asteroids that might hit us, and it was found only because it happened to be unusually large and unusually active. Countless smaller, fainter objects have surely passed through the inner solar system in recent decades, undetected, because nothing capable of seeing them happened to be looking in the right place. Rubin will be looking everywhere, all the time, and it will go deep. Predictions for how many interstellar objects it will detect vary. The population estimates carry large uncertainties, which is exactly the problem the mass budget discrepancy highlights. But the expectation is somewhere between a handful and several dozen over the decade, with some estimates running higher. Whatever the exact number, we are moving from a sample of 3 to a sample large enough to do statistics. And statistics is what this field desperately needs. Right now, every conclusion about interstellar objects rests on individual cases, and individual cases can always be dismissed as freaks. Is 3I/Atlas typical of ancient thick disk debris? Or is it a bizarre outlier even among interstellar objects? With one example, there is no way to know. With 30, the question becomes answerable. The scientific questions that a population would settle are precisely the ones this object raised and could not resolve. Are carbon dioxide-dominated comets common among interstellar objects? Or was this one unusual? Do interstellar objects preferentially come from old metal-poor stars? as the isotopes here suggest, or was this an accident of one detection? Is the extreme deuterium enrichment a general feature of material formed in the early galaxy, or a peculiarity of one disk? Do interstellar objects show the same extraordinary metal production? And if so, what does that say about the abundance and structure of their dust? Is the number density really as high as 3 detections in 8 years suggests? Or have we been fooled by small number statistics into a population estimate that violates the galaxy's mass budget? Every one of those questions has a clear observational answer waiting on the other side of a decent sample size. And the sample is coming. There is a second reason Rubin matters, and it is more practical. Early detection buys time. 3I/Atlas was found 4 months before perihelion, and that was considered generous. It was enough time to schedule Webb to organize the very large telescope campaigns, to improvise the Mars observations. It was not remotely enough time to launch anything. A wide, deep, continuous survey has a chance of catching an inbound object much earlier, while it is still beyond Jupiter, perhaps a year or 2 out, faint and inactive but detectable. And a year or 2 of warning is the difference between watching and going. Which brings us to the most ambitious idea in the field, and one of the strangest spacecraft ever built. The European Space Agency has built a spacecraft to visit a comet that does not exist yet. The mission is called Comet Interceptor, and its design philosophy is the inverse of every planetary mission ever flown. Normally, you pick a target, calculate a trajectory, design instruments around what you expect to find, and launch on a precisely timed window. Every step depends on knowing where you are going. Comet Interceptor will launch without a destination. It is scheduled to fly in the late 2020s, and on launch it will travel to the first Sun-Earth Lagrange point, a gravitational parking spot about 1.5 million kilometers from Earth on the sunward side, where an object can loiter with minimal fuel. And there it will wait, for years if necessary, dormant, fueled, ready. Meanwhile, on the ground, the Rubin Observatory and every other survey will be scanning. And when they find the right target, a long-period comet arriving from the Oort cloud on its very first pass toward the Sun, never before warmed, chemically pristine, or, in the mission's most exciting scenario, an interstellar object with a trajectory the spacecraft can reach, Comet Interceptor will wake up, leave its parking spot, and fly to intercept. The spacecraft is not one vehicle but 3. A main craft carries 2 smaller probes, and shortly before the encounter it releases them. All 3 fly through the comet's environment on slightly different paths, taking measurements simultaneously from 3 separated points. This is a clever solution to a real problem. A fast flyby gives you a single slice through a comet's coma, and a single slice is ambiguous. You cannot tell whether a feature is a real structure or a temporary fluctuation. 3 simultaneous slices from 3 positions let you reconstruct the 3-dimensional structure of the coma and its interaction with the solar wind for the first time. The smaller probes will fly closer to the nucleus, into the more dangerous region, and they are expected to be damaged or destroyed by dust impacts. They are designed to be expendable. They will transmit what they can, for as long as they last. If Comet Interceptor manages to reach an interstellar object, and this is a possibility rather than a plan, since it depends on one appearing with an accessible trajectory during the mission's operational lifetime, it would be the first time humanity has flown a machine to material from another star system. That would change everything about the quality of the data. Remote spectroscopy, magnificent as it is, has hard limits. From Earth we measure what leaves the object, filtered through the physics of the coma, integrated over the entire visible cloud. We infer the nucleus indirectly. We never see the surface. A flyby gives you images of the actual nucleus. Its shape, its size, its rotation, its color, its craters and vents and fractures. It gives you in situ measurements of the gas and dust, sampled directly rather than inferred from light. It gives you magnetic field measurements, plasma measurements, dust particle counts, and compositions. For 3I/Atlas, a flyby would have settled the mass budget question in an afternoon by simply measuring how big the thing actually was. But there is an obstacle in the way of all of this, and it is worth confronting honestly, because it is the fundamental barrier to studying interstellar objects, and it is not going away. Speed. 3I/Atlas entered our solar system at roughly 60 kilometers per second relative to the Sun. Spacecraft do not move like that. The fastest object humans have ever launched away from Earth, New Horizons, left at about 16 kilometers per second. Voyager 1, after 48 years of travel and multiple gravity assists, is receding at about 17. The interstellar objects are arriving 3 to 4 times faster than our fastest departing probes. This means a rendezvous matching velocity and flying alongside, as Rosetta did with Comet 67P for 2 years, is not merely difficult. With chemical propulsion, it is impossible. The change in velocity required, what engineers call delta V, is far beyond anything current or near-future propulsion can deliver. Rosetta needed 10 years and 4 gravity assists to catch a comet moving at solar system speeds. Catching something moving at 60 kilometers per second on a hyperbolic path that will never return would require a propulsion system nobody has built. So a flyby is the realistic option, and a flyby past an object with a relative velocity of 50 or 60 kilometers per second is an extraordinarily violent event. At that speed, you traverse the entire useful observing region in minutes. Instruments must acquire, track, and record a target moving across the field of view faster than any planetary encounter has ever demanded. And every dust grain the spacecraft meets arrives with the kinetic energy of a bullet. A grain of sand at 60 kilometers per second carries roughly the energy of a rifle round. The JWST spacecraft was hit during its 1986 flyby of Halley and was knocked off its stabilized orientation, losing its camera. It survived, barely, and its images of a comet nucleus made history. Sample return, bringing a piece of interstellar material back to Earth for analysis in a laboratory, which would be worth more than every remote observation combined, is, for the foreseeable future, out of reach. The delta V requirements are simply prohibitive. Concepts exist for the far term. Solar sails, which need no propellant and could in principle accelerate a light spacecraft to high speeds over long periods. Nuclear electric propulsion. Statite architectures that park a sail-equipped probe in a position to drop toward the sun and use a close solar pass for an enormous velocity boost, the so-called Oberth maneuver. Directed energy propulsion, where ground-based lasers push a sail. Some of these are technically plausible. None is close to flight. For now, and probably for decades, our access to interstellar material will be through light. We will read these objects rather than touch them, which is, when you consider what has been achieved by reading alone, less of a limitation than it sounds. It is worth stepping back to appreciate the machinery of what happened here, because the science of 3I/Atlas is also a story about how discovery actually works in the 21st century, and it does not look like the popular image. There was no lone genius. There was no eureka moment in a darkened observatory. What there was, instead, was a distributed global apparatus of enormous complexity, operating on a timescale of weeks, involving hundreds of people who mostly never met. It began with automation. The Discovery Telescope had no human being present. ATLAS, the Asteroid Terrestrial Impact Last Alert System, is a network of small telescopes funded primarily by NASA's Planetary Defense Program, built for a specific and rather grim purpose: to provide a few days or weeks warning of an asteroid on a collision course with Earth. It is insurance. The fact that it also finds comets, including the most scientifically important comet of the decade, is a byproduct. Within hours of the initial detection, the observation went into the Minor Planet Center, the international clearinghouse operated under the auspices of the International Astronomical Union, which has coordinated the tracking of small solar system bodies since 1947. This database is open. Anyone can query it. Archival images were mined. Recovery observations were extracted from data taken days earlier by other surveys, and the orbit was refined by multiple independent groups within a day. Then came the scramble for telescope time, and this is where the system showed its best face. The largest observatories operate on rigid schedules planned many months ahead, with oversubscription rates often exceeding 5-to-1. But every major facility maintains a mechanism for exactly this situation: director's discretionary time, a reserve that can be allocated immediately by the observatory's leadership for urgent, unrepeatable events. Proposals were written in days. Approvals came in days. Observing programs that would normally take a year to arrange were running within weeks. The James Webb Space Telescope observed 3I/Atlas on the 6th of August, 36 days after discovery. That is an extraordinary institutional response for an instrument with a multi-year proposal cycle and a queue of the most competitive science in the world. Then the results went up on AR-14, the preprint server, often within days of the observations and typically before peer review was complete. Astronomy has operated this way for 3 decades, and for a fast-moving event, it is indispensable. A team measuring nickel could see the carbon dioxide result immediately. A team modeling the trajectory could see the outgassing rates. The community was reasoning collectively in near real time in public, and it was genuinely international. The Chilean facilities operated by a European consortium, American space telescopes, a European mission at Mars, ground-based observatories in Hawaii, in the Canary Islands, in South Africa, in Chile, in Arizona, radio observatories in multiple countries, teams with authors from dozens of institutions across every inhabited continent. Amateurs mattered too, and not in a token way. The global network of skilled amateur astronomers, people with serious equipment, careful technique, and often decades of experience, contributed astrometry that tightened the orbit and photometry that filled the light curve on nights when no professional facility was scheduled. Comet science has depended on this community for 2 centuries and still does. And running underneath all of it was the unglamorous infrastructure that makes any of it possible. The reference catalogs, the calibration standards, the fluorescence models built up over decades of laboratory work, the archived spectra of solar system comets that made comparison meaningful, the software pipelines, the data formats, the peer-reviewed literature stretching back to Whipple and beyond. When the carbon dioxide result came in, the reason anyone could recognize it as extraordinary was that hundreds of researchers had spent 50 years patiently measuring ordinary comets. The anomaly was only visible against a background of accumulated normality, and that background represents an immense amount of careful, largely uncelebrated work. That is what made it possible to characterize a 10-billion-year-old fragment of another star system in 18 months. Not brilliance in a single mind, but a civilization-scale instrument assembled over centuries, operating faster than any individual could think. And it is worth noting how much of the essential work was done with tools built for something else entirely. A planetary defense survey found it. A sky mapping mission not designed for comets confirmed the carbon dioxide and discovered the water ice. Mars orbiters built to study a planet's atmosphere turned outward to photograph a comet. A gamma-ray burst satellite watched it in the ultraviolet. Astronomical infrastructure is repurposable in a way that is easy to overlook, and when something genuinely unexpected arrives, that flexibility is what saves you. Because the truth is that nothing about 3I/Atlas was planned for. It simply arrived on its own schedule, indifferent to ours, and the world had a matter of weeks to decide what to do about it. Which raises a question that occurs to almost everyone the first time they hear about these objects, and which deserves a clear answer. Could one of them hit us? The short answer is that 3I/Atlas never came anywhere near Earth. Its closest approach was around 1.8 astronomical units, roughly 270 million kilometers, nearly twice the distance from the Earth to the Sun. It was never a threat in any sense, and the various rumors that circulated online during 2025 suggesting otherwise had no basis in the orbital data, which was public, precisely determined, and available to anyone who wanted to check. The longer answer is more interesting, and it is the reason the telescope that discovered it exists in the first place. Atlas was built for planetary defense. So were Pan-STARRS, which found ʻOumuamua, and the Catalina Sky Survey and several other programs. Their purpose is to detect objects on Earth-crossing trajectories in time to do something about it, and they have collectively found and cataloged tens of thousands of near-Earth asteroids. This is one of the very few areas where humanity has actually organized itself to address a low-probability, high-consequence natural hazard in advance, and it works. Interstellar objects are a small addition to that risk picture, but they are a qualitatively different one for 2 reasons. First, speed. A typical asteroid impact occurs at perhaps 15 to 25 kilometers per second, because the impactor is bound to the Sun and moving at solar system speeds. An interstellar object would arrive far faster. Kinetic energy scales as the square of velocity, so an interstellar body would deliver something like 4 to 9 times the energy of an equivalently sized asteroid. A modest object could hit with the force of a much larger one. Second, warning time. Near-Earth asteroids are on closed orbits, which means they come back, which means they can be cataloged once and tracked indefinitely. An interstellar object appears once, arrives from an unpredictable direction, moves fast, and is often faint until it becomes active. Detection windows are short. Now the reassuring part, which is genuinely reassuring. The probability is extremely low. Space is overwhelmingly empty, Earth is a very small target, and even with population estimates in the trillions per relevant volume, the frequency of interstellar impacts on Earth over geological time is thought to be very small compared to the flux of ordinary asteroids and comets. Ordinary near-Earth objects remain, by a wide margin, the dominant hazard, and even that hazard is modest on human timescales. There have been claims of detected interstellar meteors, small objects that burned up in Earth's atmosphere with velocities suggesting an unbound origin. And those claims have been contested, since meteor velocity measurements carry substantial uncertainties, and an error of a few kilometers per second can move an object across the boundary between bound and unbound. It is plausible that small interstellar particles strike Earth regularly. It is not established. So the practical picture is this. Interstellar objects are not a significant addition to the risk we already manage, but they are a reminder that our surveillance of the sky is recent, incomplete, and worth continuing. The same infrastructure that protects us is the infrastructure that discovers these things. Planetary defense and pure science are, in this case, the same telescopes doing the same work, and the scientific windfall from 3i/Atlas is a direct dividend of a program funded to prevent an entirely different outcome. There is also a version of this question that is not about danger at all, and it is more appealing. What if one arrived on a trajectory that brought it close? Because a close pass, a genuinely close pass inside the moon's distance or even within a few million kilometers, would be a scientific event beyond anything in this story. Radar could measure the nucleus directly, resolving its size and shape and rotation and eliminating the uncertainty that currently undermines half the conclusions drawn about 3i/Atlas. Optical telescopes could resolve surface features. A hastily launched spacecraft might even be able to reach it. That will happen eventually. If interstellar objects pass through the inner solar system as often as the estimates suggest, then over the coming centuries some will come close, and the surveys will find them, and by then the response capability may exist. For now, the thing to appreciate is that a modest half-meter telescope, funded to look for rocks that might hurt us, produced one of the most significant scientific discoveries of the decade by accident, and that this is not unusual. The history of astronomy is largely a history of instruments finding what they were not built to find. Penzias and Wilson discovered the cosmic microwave background while trying to eliminate noise from a radio antenna. Jocelyn Bell Burnell discovered pulsars while checking for interference in a scintillation survey. The infrastructure of observation, once built, has a way of returning far more than was asked of it. 3i/Atlas is the latest entry in that ledger, and it may be the most valuable one of this century so far. Here is an honest inventory of what we still do not know, because a documentary that ends with everything solved is a documentary that is lying to you. We do not know how big it is. This sounds absurd. We watched it for a year and a half with the finest instruments ever built. But it is true, and it is the single most consequential gap. The nucleus was never directly seen. It was buried inside its own coma from before discovery until long after departure. A solid body hidden inside a glowing cloud thousands of kilometers across. Every size estimate is an inference. Model the dust, model the gas, subtract the coma's contribution to the brightness, and see what solid surface is required to produce the observed activity. The answer depends on assumptions about albedo, about grain properties, about the fraction of the surface that is active. Published estimates spanned a range from a few hundred meters to several kilometers, a range of roughly a factor of 10 in radius, which is a factor of 1,000 in mass. A 1,000-fold uncertainty in the mass of the best-studied interstellar object in history. That is where the mass budget crisis lives, and it will not be resolved by more remote observation. It requires either a flyby or radar or a lucky occultation. We do not know its shape or its rotation with confidence. Ground-based photometry gave hints of periodic variation, but disentangling a nucleus light curve from the variable brightness of an actively outgassing coma is treacherous, and the results were not decisive. We do not know whether it is representative. This is the deepest uncertainty of all. Every strong conclusion in this story, about metal pore origins, cold formation, ancient galactic chemistry, rests on one object. Is 3i/Atlas a typical member of a vast interstellar population? Or is it a freak, the one weird object out of trillions that happened to wander past a species capable of noticing? 3 data points, all radically different from one another, is not a distribution. It is an anecdote with error bars. We do not know why the carbon dioxide enrichment is so extreme. The 2 leading explanations, formation near the carbon dioxide snowline, or billions of years of radiation processing, are both plausible, both consistent with the data, and neither has been isolated. It may be both. It may be something we have not thought of. We do not know why the metal production was 10 times anything ever measured. The nickel-to-iron ratio question was answered. The absolute abundance question was not. We do not know what mechanism ejected it. Interaction with a giant planet is the standard answer, but there are alternatives. The death of its star and the resulting mass loss, which loosens the gravitational grip on distant bodies and releases them. A close stellar encounter stripping the system's outer reservoir. A binary companion's chaotic influence. We do not know how it survived. 10 billion years is a long time to remain a coherent body. Thermal cycling, cosmic ray erosion, micrometeoroid bombardment, and the slow sublimation of volatiles into vacuum should all act to degrade it. Its survival as a still volatile-rich object across that span constrains models of interstellar erosion, and the constraints are not comfortable. We do not know whether the deuterium value applies to its bulk composition or only to the water that happened to be venting when we looked. Comets are heterogeneous. Different vents can tap different reservoirs. And we do not know and will never know where it came from. That door is closed permanently. There is something valuable in stating all this plainly. The popular presentation of science tends toward resolution. The mystery is posed, the investigation proceeds, the answer arrives, the credits roll. Real science accumulates a growing pile of better formulated questions. What 3i/Atlas delivered was not a set of answers. It was a dramatic upgrade in the quality of our confusion. Before July 2025, we did not know that interstellar objects could be radically different from local comets in their volatile chemistry. Now we know they can, and we do not know how often. Before 2026, we did not know that material formed around old metal-poor stars carries isotopic signatures this extreme. Now we do, and we do not know what that implies for planet formation in the early galaxy. Before this encounter, nobody had noticed that our population estimates for interstellar objects might violate the galaxy's heavy element budget. Now that contradiction sits in the literature, unresolved, waiting. Those are better problems than the ones we had. That is what progress looks like most of the time. And where is it now? By the time you hear this, 3i/Atlas is somewhere in the outer solar system on its way out, and it will never come back. Its outbound path carries it away from the sun on the other branch of its hyperbola, still traveling at tens of kilometers per second and still decelerating slightly as the sun's gravity pulls at it. But the deceleration is temporary and insufficient. The object arrived with excess velocity and it will depart with excess velocity, asymptotically approaching a final speed of something like 60 kilometers per second relative to the sun as it climbs out of reach. It will cross the orbit of Jupiter, then Saturn, then Uranus and Neptune, its coma shrinking and then vanishing entirely as the sunlight weakens below the threshold that drives its chemistry. The carbon dioxide will stop venting. The water ice grains will stop lofting. The metals will stop escaping. The object will go quiet and dark, a cold lump again, as it has been for almost all of its existence. It will pass through the Kuiper belt without noticing it. It will pass through the Oort cloud, a journey of tens of thousands of years just to cross that vast shell of icy bodies. And it will not be captured because nothing out there is massive enough to capture anything. Within about 100,000 years, it will be a light year away, at the boundary where the sun's gravitational influence gives out and the galaxies takes over. After that, it resumes the life it had before us, a solitary orbit around the center of the Milky Way, another 200 million year lap, rising and falling through the galactic plane, drifting. It will almost certainly outlast us. It will outlast our civilization by an enormous margin, and it may well outlast our species, and it will probably outlast our sun, which has about 5 billion years left before it swells into a red giant, consumes the inner planets, and collapses into a slowly cooling white dwarf. By then, 3i/Atlas will be roughly 15 billion years old and will have completed another 25 circuits of the galaxy, and it will still be a lump of ancient ice moving through the dark. The encounter is over, and it was, in cosmic terms, almost unimaginably brief. Think about the timing that had to hold for this to happen at all. The object spent 10 billion years in interstellar space. It spent, at most, about 2 years within observational range of Earth. That is a ratio of roughly 1 part in 5 billion. If our species had arisen 2,000 years later, we would have missed it entirely. If the telescope in Chile had not been built, or had been pointed elsewhere, or had been clouded out that night, we might have missed it. If it had arrived in 1975, before digital detectors and automated surveys, it would have passed through the solar system, vented its extraordinary chemistry into space, and departed with no one on Earth ever knowing it was here. And that has certainly happened, repeatedly. If the population estimates are even roughly correct, interstellar objects have been passing through the inner solar system throughout human history, during the construction of the pyramids, during the Roman Empire, during the lifetime of every person who ever lived, and every one of them went unnoticed because we had no way to see them and no idea to look for them. We spent our entire history as a species inside a solar system that is continuously visited by material from other stars, and we found out about it in 2017. That fact should be held carefully, because it is not really about comets. It is about how recent our capacity to notice things actually is, and how much must have passed unobserved. There is another way to hold the brevity of the encounter, which is to notice what it demanded of the people involved. Astronomers who study interstellar objects have exactly 1 shot at each one. There is no going back for a second look, no follow-up campaign next season, no waiting for better instruments. The object arrives, you observe it with whatever exists at that moment, and then it is gone forever, and your data is all that will ever exist. Every observation of ʻOumuamua that was not made in those 11 days is an observation that can never be made by anyone, ever, for the rest of time. That is a rare kind of pressure. Most of astronomy is patient. The stars will still be there next year. This is not that. This is a discipline conducted entirely in the imperative, against a deadline set by orbital mechanics, with no possibility of correction. They did well. In 18 months, working under those constraints, they determined that this object formed below 30 Kelvin, around a metal-poor star, in a galaxy roughly 10 to 12 billion years old, with a volatile inventory inverted relative to every comet in our system, an unprecedented metal content, and a chemical composition that has forced a general reassessment of how universal our own origins are. That is not a bad haul for a smudge of light that showed up unannounced. There is a particular kind of vertigo that comes from handling something older than the ground you stand on, and it is worth sitting with because it is the emotional center of this whole story. Human beings are not built for deep time. Our intuitions are calibrated to seasons and lifetimes. A century feels long. 1,000 years feels almost mythological, the distance back to the Viking voyages, to the Song dynasty, to a world before printing. 10,000 years takes us to the beginning of agriculture, which is functionally the beginning of everything we recognize as human civilization. Now stretch that. The oldest rocks on Earth are about 4 billion years old. The oldest fossils of life around 3.5 billion. Complex animals 600 million. The dinosaurs 230 million years ago, gone 66 million years ago. The first hominins that walked upright perhaps 6 million. Anatomically modern humans 300,000. 3I/Atlas is, by the best available evidence, somewhere between 7 and 12 billion years old. Try to put those on the same line and the human entries disappear. If the age of this object were compressed into a single calendar year, our species would appear in the last 5 minutes of the 31st of December. Recorded history would occupy the final 10 seconds. The telescope that found it would be built in the last fraction of the last second. And in that fraction of a second, the creatures who built it determined the temperature of the cloud in which it condensed, the isotopic composition of its water, the age of the galactic material from which its carbon was drawn, and the approximate epoch of the star that made it and lost it. There is something almost impertinent about that. A species that has existed for an eye blink, on a planet that did not exist when this object was already ancient, using instruments invented within a single human lifetime, reached out and read a document written 10 billion years ago in a language of light. But the vertigo cuts the other way too, and this is the part that I think matters more. For most of history, the sky was a fixed and separate thing. Whatever it was made of, it was not made of the same stuff as us. The medieval cosmos had a hard boundary at the moon. Below, the corruptible world of the four elements. Above, the incorruptible quintessence, unchanging and eternal and categorically other. That distinction survived until the 17th century, when Galileo saw mountains on the moon and spots on the sun, and it took another 200 years to fully collapse. What collapsed it, ultimately, was chemistry. In 1859, Gustav Kirchhoff and Robert Bunsen demonstrated that the dark lines in the solar spectrum correspond to the emission lines of elements they could burn in a laboratory in Heidelberg. Sodium in the sun was the same sodium as sodium in a flame on a bench. That single realization is the foundation of everything in this story. The philosopher Auguste Comte had declared, a few decades earlier, that the chemical composition of the stars was an example of knowledge forever beyond human reach. He was catastrophically wrong, and he was wrong within his own century. 3I/Atlas is the furthest extension of Kirchhoff's insight yet achieved. We have now performed chemical analysis, including isotopic analysis, which is a far finer thing, on material that condensed in another star system, in another era of the galaxy, and drifted here across 10 billion years. And what we found was carbon and oxygen and hydrogen and nitrogen and nickel and iron and sulfur, arranged into water and carbon dioxide and carbon monoxide and cyanide and methanol and carbonyl sulfide. The proportions were unfamiliar. The isotopes were unfamiliar. But the alphabet was identical. That is not a small result. It is the confirmation at the most direct level possible that the chemistry which produced us is not a local dialect. The same molecules assemble on cold grains in every corner of this galaxy, in every era, around metal-poor stars and metal-rich ones alike. The universe uses one set of ingredients, and it has been using them since long before Earth existed. We are, quite literally, made of the same materials as an object from another star, formed under a different sun, before our sun existed. The atoms in your body were forged in stars that died before the sun was born, and the atoms in 3I/Atlas were forged in a different set of stars that also died before the sun was born, and in both cases the resulting chemistry made water and organic molecules and complex mineral grains, because that is what this universe does with those ingredients when you leave them alone in the cold and the dark for long enough. That is the deepest finding of this whole affair, and it survives every argument about what the numbers mean. Not that the galaxy is full of life. We have no evidence of that from this object or any other, but that the galaxy is full of the same chemistry, running everywhere, continuously, for the entire history of the universe, in every place cold enough and dark enough and old enough to let it run. Which forces one final reconsideration, and it is about our own position. For most of the 20th century, planetary science was in an epistemic trap that its practitioners fully understood and could do nothing about. They had one solar system. They could study it in extraordinary detail, send probes to every planet, land on Mars and Venus and Titan and a comet, return samples from the moon and an asteroid in the solar wind, but they could not know how much of what they found was general and how much was particular to us. It is the problem a scientist would face trying to write the biology of life on Earth from a single organism. You could study that organism exhaustively. You could sequence it, dissect it, understand every metabolic pathway. And you would still have no way of knowing which features were universal to life and which were peculiar to that one creature. Our solar system was that organism, and its findings were generalized into laws because there was nothing else to generalize from. The last 30 years have been a systematic dismantling of that generalization. Exoplanets showed that our architecture is not standard. Now interstellar objects are showing that our composition may not be either. 3 data points is not a lot, but here is what they already establish. ʻOumuamua was so unlike a comet that we could not classify it. Borisov was so like a comet that it was reassuring. 3I/Atlas is unmistakably a comet and unmistakably unlike ours. Inverted volatile chemistry, isotopes 10 times outside our entire measured range, metal production an order of magnitude beyond anything recorded, an age that predates our sun by billions of years. The spread across 3 objects is enormous. Whatever the population of interstellar objects looks like, it is not a narrow distribution centered on solar system comets. It is wide, and we are somewhere in it, and we do not yet know where. That is a genuinely humbling result, and it comes with a genuinely exciting corollary. Every one of these objects is a free sample from a star system we could never otherwise study. We cannot travel to other stars. The distances forbid it with any technology we can currently imagine. Even the nearest Proxima Centauri is 4 light-years away, a journey of tens of thousands of years with chemical propulsion. Direct exploration of another planetary system is not on the table for any foreseeable future. But other planetary systems have been sending us pieces of themselves, continuously, for as long as they have existed. We did not have to go anywhere. We simply had to learn to notice. That is what changed in 2017, and what was confirmed in 2019, and what was spectacularly demonstrated in 2025 and 2026. Interstellar space is not a barrier that isolates us. It is a medium through which material moves, slowly and in tiny quantities and over enormous timescales, but continuously and in all directions. The galaxy delivers. And now, at last, we can read the mail. Consider what this means for the coming decades. Vera Rubin begins its 10-year survey. Interstellar objects start appearing at a rate we can do statistics on. For each one, we measure volatile chemistry, isotopic ratios, dust properties, kinematics. From the kinematics, we get an approximate age and a stellar population. From the isotopes, we get a formation temperature and a galactic epoch. From the chemistry, we get a formation location within a disk we cannot see. Assemble a few dozen of those, and something entirely new comes into existence. A comparative chemistry of planetary systems across the history of the Milky Way. A record of how the raw material of worlds has changed as the galaxy aged, sampled directly from objects that formed in eras we cannot otherwise touch. That field does not exist yet. In the 2030s it will. And when the textbooks of that discipline are written, the chapter on its founding will begin with a half-meter telescope in the Atacama Desert, on the 1st of July 2025, noticing that something had moved. Before the summing up, it is worth setting the 3 visitors beside one another, because the comparison is itself a result. ʻOumuamua came in 2017. Small, a few hundred meters, wildly elongated or wildly flattened, tumbling chaotically, showing no coma, no gas, no dust, no visible activity of any kind, and yet accelerating as it left, pushed by something invisible. Detected on its way out, studied for 11 days, gone forever with its nature unresolved. It remains nearly a decade later, genuinely unexplained. The leading natural hypotheses require it to be made of something exotic, hydrogen ice, nitrogen ice, or a structure so porous it barely counts as solid. 2I/Borisov came in 2019. Unmistakably a comet, active, dusty, tailed, discovered inbound by an amateur with a homemade telescope. Its chemistry was broadly familiar, water-driven, with cyanide and diatomic carbon, somewhat enriched in carbon monoxide, with an odd nickel abundance. It was studied properly, it behaved reasonably, and the lesson everyone took was that the galaxy makes comets like ours. 3I/Atlas came in 2025. Large, bright, spectacularly active from beyond Jupiter, discovered 4 months before perihelion, and observed continuously for a year and a half by every major instrument on and off the Earth. Its chemistry was inverted. Its isotopes were off the scale. Its metals were unprecedented. Its age exceeds that of the solar system by billions of years. 3 objects. 3 completely different characters. One inexplicable, one familiar, one alien in exactly the ways that matter most. If you had to summarize what these 3 have taught us in a single sentence, it would be this: interstellar objects are not a category with a typical member. They are a sample drawn from the entire population of every planetary system that has ever existed in this galaxy, across the whole of cosmic history, and that population is enormously diverse, which is, on reflection, exactly what it should have been. We knew the galaxy contained hundreds of billions of stars of every mass and metallicity and age. We knew planetary systems form under wildly varying conditions. We knew, from 30 years of exoplanet science, that their architectures vary enormously. Why on earth would their debris be uniform? The expectation of uniformity was never a finding. It was a habit, the natural consequence of having only one example and no reason to imagine otherwise. And what these 3 objects have done, more than any individual measurement, is break the habit. There is a useful discipline in noticing when that happens, because it happens rarely and it is easy to miss. Most scientific results refine an existing picture. Occasionally one arrives that reveals the picture had an unexamined frame around it. The heliocentric model did that. Deep time did that. Galaxies beyond our own did that. The discovery that our solar system's chemistry is provincial rather than universal is a smaller version of the same move, and it belongs to the same family. Each one takes something we assumed was the whole and reveals it as a part. We are, it turns out, one solar system among an enormous variety of solar systems, made of one particular mixture of a universal set of ingredients, formed at one particular moment in a galaxy that has been changing chemically for 13 billion years. That was always true. As of 2025 and 2026, we have physical evidence of it in our hands, or at least in our archives. So let us gather what we have and be precise about it, because precision is the only honest form of wonder. On the 1st of July, 2025, an automated telescope in the Chilean desert detected a moving point of light beyond the orbit of Jupiter. Within days, orbital analysis revealed an eccentricity slightly above 6, a number so far past the boundary of gravitational capture that there was no ambiguity at all. The object was not from here. It had never been from here. It was falling through, and it would leave, and nothing in our solar system could hold it. It was named 3I/Atlas, the third confirmed interstellar object in the recorded history of our species. Over the following 18 months, the most capable observatories ever constructed by human beings examined it in every wavelength available to us, and what they found was a chemistry unlike anything in our solar system. The James Webb Space Telescope, observing at 3.32 astronomical units, found a coma dominated by carbon dioxide, with a carbon dioxide to water ratio of 7.6, among the highest ever measured in any comet, 4.5 standard deviations above the trend defined by the entire studied cometary population. Water, the substance that defines cometary activity in our system, was a minority component, and much of it was not sublimating from the nucleus at all but evaporating from a cloud of ejected ice grains carried off by the pressure of escaping carbon dioxide. The hierarchy of a comet was inverted. Alongside the carbon dioxide came carbon monoxide, solid water ice in large quantities, dust, carbonyl sulfide, hydrogen cyanide, methanol in unusually high proportion, and a substantial inventory of complex organics that emerged only after perihelion, when solar heating had penetrated past the processed outer crust into the pristine material beneath. High-resolution spectroscopy at the Very Large Telescope found atomic nickel in the coma at distances where no thermal process could possibly vaporize metal, and, at first, no iron at all. The most likely mechanism is a class of low-temperature organometallic chemistry, related to the industrial process discovered by Ludwig Mond in 1890, in which carbon monoxide carries nickel away as a volatile compound while leaving iron behind. As the object warmed, iron appeared and the ratio normalized to ordinary cometary values, but the total production of metal vapor remained at least 10 times greater than that of any comet ever measured. And then the isotopes, which settled everything. The water in 3I/Atlas carried a deuterium to hydrogen ratio of 0.98%, more than an order of magnitude above any comet in our solar system, outside the entire measured range of every body humanity has ever sampled. That level of deuterium enrichment can only be produced by ion molecule chemistry at temperatures at or below 30 Kelvin. The carbon-12 to carbon-13 ratio, measured independently in carbon dioxide, in carbon monoxide, and in cyanide, ran from roughly 123 to 191, exceeding the solar system value of 89, exceeding local interstellar clouds, exceeding the protoplanetary disks we observe around young stars today. Galactic chemical evolution models place that composition in the Milky Way of 10 to 12 billion years ago. The nitrogen-14 to nitrogen-15 ratio came in near 343, more than double the value of about 150 that holds with remarkable consistency across every comet in our solar system, and much closer to the values of the raw interstellar medium and the outer edges of protoplanetary disks, indicating formation far from its star in a weak ultraviolet field. And the object's motion, measured entirely independently of any of this chemistry, placed it kinematically among the ancient stars of the Milky Way's thick disk. For separate measurements by 4 separate teams, using 4 separate physical principles, converging on one conclusion, 3I/Atlas formed at temperatures below 30 Kelvin, in the frozen outer reaches of a protoplanetary disk, around an old and metal-poor star, at a time when our galaxy was young and our sun did not exist and would not exist for billions of years. Then something threw it away, and it drifted, and after a journey longer than the age of the Earth, it happened to pass a small blue planet at the exact moment in that planet's history when its inhabitants had learned to read light. That is what we found. That is the whole finding, stated plainly, and it does not need embellishment. And so, finally, to the question in the title, answered properly. Are scientists rewriting the laws of physics? No, and the truth is better. The laws of physics were not merely intact through all of this. They were the instrument. It was quantum mechanics that let us identify carbon dioxide by the precise energy of a vibrational transition. It was the physics of isotopic fractionation that let us read a formation temperature from the ratio of two forms of hydrogen. It was nuclear astrophysics and galactic chemical evolution that let us convert a carbon isotope ratio into a date 10 billion years in the past. It was Newton and Kepler and Einstein who let us take 3 points of light on a photographic plate and declare with certainty that this object came from beyond the sun's reach. The laws did not break. The laws were how we knew. What is being rewritten is the story we told using those laws, the model of how planetary systems form, what they are made of, and how much our own experience can be trusted as a guide to the rest. That model was built from a sample of 1 and quietly generalized to 100 billion. And it is now demonstrably too narrow. We assumed comets were water first everywhere. This one was carbon dioxide first by a factor of 8. We assumed isotopic ratios in planetary material fell within a range we had mapped. This one sat 10 times outside it. We assumed the raw ingredients of worlds were roughly constant across cosmic time. This one came from a galaxy chemically unrecognizable compared to ours. We assumed our solar system's inventory of building material was a closed system. It is not and never was. Those are not laws. They are assumptions, the invisible scaffolding that surrounds every science built on a limited sample. And the demolition of unexamined assumptions is not a crisis for a field. It is the single most productive thing that can happen to one. What is genuinely being rewritten, then, is the scope of planetary science. Not its rules, but its subject matter, which has just expanded from one solar system to the entire history of a galaxy, and from 4.5 billion years to more than 10. And here is the thing about that. It is happening now. Not in a textbook, not in retrospect, but in real time, in papers being written and argued over and revised as this is spoken. The mass budget contradiction is open. The size of the nucleus is unresolved. The origin of the carbon dioxide excess is undecided. The question of whether this object is typical or freakish will not be answerable until the Rubin Observatory has been running for years. There is a version of science communication that presents the field as a finished edifice, a body of settled knowledge to be admired from a distance. That version is comfortable and false. The reality is that at the edges, and the edges are where everything interesting lies, the whole thing is provisional, contested, and moving. Scientists are people in the middle of an argument, and the argument is not resolved, and that is not a weakness of the enterprise. It is the enterprise. 3I/Atlas is a snapshot of that process at its best. A genuinely unexpected object, examined with extraordinary rigor by hundreds of people across dozens of countries with instruments not designed for the job, producing results that broke a model, generating a heated public controversy, and leaving behind a set of open questions sharper than the ones it found. Nobody rewrote a law of physics. What happened was harder and more valuable. A field discovered the limits of its own imagination and began immediately to expand them. There is one more thing to say, and it is not about chemistry. Every generation of humans has looked up at the same sky and seen something different, and what they saw was determined less by the sky than by what they were capable of noticing. For our ancestors on the African savanna, the sky was a clock and a calendar and a map, a reliable machine that told you when the rains would come and which way to walk. For the Babylonians, it was a text to be decoded, the intentions of gods written in the motions of planets. For the Greeks, it was geometry, nested crystalline spheres of perfect proportion. For the medieval world, it was a hierarchy, ascending in purity toward a divine center. For Newton, it was a mechanism obeying equations that also governed a falling apple. For us, in the 21st century, it has become something no previous generation could have conceived: an archive. a place where objects far older than our planet are still in motion, still carrying intact the chemical record of environments that vanished before the Earth condensed, and still occasionally passing close enough to read. That is a genuinely new relationship with the sky. Not a new sky, the same photons, the same objects, mostly the same arrangement our ancestors saw. What changed is us. And the change was fast. The spectroscope that made all of this possible dates to the 1860s. The photographic plate that let us record faint objects dates to the same era. The digital detector that made automated surveys possible was invented in 1969. The James Webb Space Telescope launched in December 2021 and was operating for barely 3 years before it turned toward 3I/Atlas. The Rubin Observatory has only just begun. Every technique used to characterize a 10-billion-year-old object from another star was developed within the last century and a half, and most of the critical ones within the last 30 years. We are the very first generation with the capacity to do this. Not the first to wonder, people have wondered forever, but the first to be able to answer. That is worth pausing on because it is easy to be blasé about it. Instruments now exist that can determine, from the color of light, whether a molecule hundreds of millions of kilometers away contains one extra neutron. That capability did not exist when your grandparents were born. Consider what it means that a species which was chipping stone tools 12,000 years ago can now perform isotopic analysis on a comet from another star system, and can do it as a matter of routine within weeks with instruments that were built for something else. And consider that the object which allowed it was here for 2 years out of 10 billion, and we happen to be looking. The thing about 3I/Atlas is that it was not a message. Nobody sent it. Carries no intention and no meaning of its own. It is a lump of frozen material that was gravitationally discarded by a star system that no longer exists, and it wandered for a span of time that our minds cannot properly represent, and it passed through here on its way to nowhere in particular. And yet it told us more about the diversity of planetary systems than any single object in the history of the field. It did that not by being a message but by being evidence. And evidence, unlike a message, cannot lie, cannot exaggerate, and does not care whether we understand it. That is why the isotopes were the heart of this story. Molecules can be argued about. Ratios of production rates depend on models. But deuterium at 1% is deuterium at 1%, and there is exactly one way for the universe to make that, and it involves temperatures below 30 Kelvin, and no amount of speculation changes it. The universe answers the questions we know how to ask. And the whole discipline of science, in the end, is the accumulated craft of learning to ask better ones, of building instruments that turn phenomena we cannot perceive into numbers we can compare, and then having the discipline to let those numbers overrule what we expected. We expected a comet like ours. We got a document from the early Milky Way. And the reason we know the difference is that when the data disagreed with the model gave way. Somewhere out past the orbit of Neptune, in the deep cold beyond any place sunlight matters, an object is moving away from our sun at 60 kilometers per second. It has gone quiet. The carbon dioxide that once poured off it in a glowing torrent has frozen still. The tiny grains of deuterium-rich water ice have stopped lifting from its surface. The nickel atoms have stopped escaping. The coma has collapsed and dispersed, and what remains is what was always there. A dark, cold, irregular lump, a few hundred meters or a few kilometers across, tumbling slowly, carrying inside it a chemistry that has not changed since a galaxy that no longer exists. It is exactly as it was before, except for one thing. It has been read. Somewhere in a data archive in Maryland, and in Chile, and in Germany, and in Japan, there are files containing the spectra of that object. They will be there long after it has gone. Students not yet born will download them and reanalyze them with techniques not yet invented, and they will extract things from that data that nobody has thought to look for yet. That is how astronomical archives work. Some of the most important results in the field have come from data taken decades earlier for entirely different reasons. The nickel and iron in ordinary comets, the discovery that upended cometary chemistry in 2021, was sitting unrecognized in archive spectra for years, invisible because no one believed it could be there. So the encounter is not entirely over. The object has left. The information stayed. And that is, in the end, the strangest and most durable form of contact our species has managed. We did not touch it. We never will. We have no idea where it came from and no way to find out. Between us and it, there was never anything but a few months of reflected sunlight falling on some very carefully made mirrors. That was enough. From that, we reconstructed the temperature of a cloud that collapsed before the Earth existed. We dated the galactic chemistry of an epoch we can otherwise only observe by looking at distant galaxies whose light has traveled for 10 billion years. We identified the industrial chemistry of a Victorian nickel refinery operating spontaneously on the surface of a frozen body from another star. We found, in an object formed under a different sun in a poorer and younger galaxy, the same hydrogen cyanide and carbonyl sulfide and methanol from which, on one particular planet, the first living things were eventually assembled. The next one is already out there, perhaps several. They are moving through the dark right now, silent and unlit, on their own trajectories, indifferent to whether anyone notices. Some of them will pass close enough to detect. Some will be detected. And in the 2030s, when the great survey telescopes are finding these things routinely rather than by accident, the strangeness of 3I/Atlas will either be confirmed as typical or revealed as unique, and either answer will teach us something enormous. But the first one that mattered, the first that arrived early enough and bright enough and active enough to be truly read, was found on a July night by a machine in the desert, doing its rounds, comparing one photograph to another, looking for something that had moved. It found a fragment of a solar system that died before the sun was born. We looked at it for 18 months and then it left. And the extraordinary thing, the thing worth carrying away from all of this, is not that its chemistry was impossible. Nothing about it was impossible. Every molecule obeyed every law. Every atom did precisely what atoms do. The extraordinary thing is that we could tell that a species so recent on a world so young, using instruments so new, could look at a smudge of light in the outer solar system and say, "This water froze below 30 Kelvin. This carbon comes from a galaxy 10 billion years younger than ours. This nickel was carried out by carbon monoxide in the cold. This thing is older than the Earth and it is not from here, and here is what it is made of." The universe is under no obligation to be comprehensible. It has simply turned out so far to be so, and the only reliable way anyone has found to keep it that way is to keep looking, keep measuring, and be willing, when something arrives that does not fit, to put down the model and pick up the data. 3I/Atlas is out there tonight, climbing away, dark and silent, carrying the rest of its secrets with it into a darkness it will not leave again for as long as this galaxy exists. We got a few of them. That is more than anyone before us ever managed. And the sky, which has been sending us these things since before there was anyone here to see them, is still full of mail we have not opened.